When we first looked at chemical reactions and we started writing out our equations to represent chemical reactions, we had four states of matter that we could use symbols for. We had S for solid, L for liquid, and G for gas. The fourth state symbol that we used was AQ, or aqueous, right? Now, this was a state of matter referencing something in aqueous solution, or dissolved in water. And in this chapter, we're going to look at homogeneous mixtures in general, okay, all of these kind of solutions, but we'll pay a special attention to aqueous solutions, especially. So, what are solutions? As I pointed out, all homogeneous mixtures are considered solutions. And if you go back to chapter 2, we first talked about mixtures in general, and specifically what homogeneous mixtures were as opposed to heterogeneous mixtures. In fact, in this chapter, we will talk briefly about heterogeneous mixtures, especially a special class of them called colloids, but I'm getting ahead of myself here. So, our homogeneous mixtures, or solutions, are formed between two or more substances, and we have special terms for the parts of our solution. The larger portion of the solution that things dissolve into is known as the solvent. And the solute refers to the smaller part of the mixture that dissolves in the solvent. Okay, so to give you an example, let's say you're making a salt solution. In this case, the salt is your solute and water is your solvent. Okay. The other way you can tell what's the difference between your solute and solvent, besides just the amount or proportion, typically, since your solvent makes a larger part of your solution's going to usually look like your solvent. So once you dissolve your solute in the water, your salt solution looks like water, looks like your solvent. Now, while the majority of solutions, when we think of the word solution, the most common example that comes to mind is an aqueous one, where we have a solid dissolved in water, which is a liquid. That being said, your solute or your solvent can be either a solid, liquid, or gas. It doesn't really matter. You can have a gas dissolved in a gas dissolved in a liquid, a solid dissolved in a gas. There's different ways that you can have a solution. It's really any homogeneous mixture. So watch out for that common pitfall where oftentimes students are locked into thinking that a solution can only be an aqueous solution. There's lots of different solutions out there. But again, the key thing here is that it's a homogeneous mixture. Your solute particles are spread evenly through your solution, and they're completely dissolved by that solvent. Okay, so it looks like one homogeneous phase. Okay, we talked about this way back in chapter 2, and we're going to go into more detail into what this means in this chapter. Now, we saw back in chapter 2 that you can separate out the parts of a mixture through some physical method. And the thing is that when you have a homogeneous mixture, some physical methods work while others don't. All right, so for example, with filtration, that's a method we could separate out the parts of a heterogeneous mixture. So for example, if you had sand and water, okay, now the sand won't dissolve in the water. Those sand particles are just too big to be sort of dissolved into the water, and so they form what's called a suspension. Okay, again, we'll talk a little bit more about suspensions along with colloids later on in this chapter. But we could filter out the sand, right? Our filter has small enough pores that they would trap the sand particles and leave behind just the water. With a solution, you can't do that. Okay, you can't filter out the solute in a solution. It's dissolved in the solvent, so it can't really be picked up by the filter. That being said, other physical methods such as distillation, which involves evaporating the solvent, evaporating your water and having it, condense somewhere else. That's an example of a physical method you could use to separate out the parts of a solution like that. Okay. Now I mentioned that again, your mixture will look like your solvent. So in the case of aqueous solutions, at least, your solution will look like water. Okay. Now that being said, just because you don't see your solute particles, and we'll talk about why that is, that doesn't mean it can't change certain properties. So, for example, water is transparent, right? It's water light passes through it. It's clear, so to speak. And when you have a solution, it's going to have that same property. However, solutes can change the color of a solution. All right. This is why when you describe water as clear and colorless, you have to remember those are not the same thing. Okay, so for example, if we take copper 2 sulfate, which is this bright blue solid, it's an ionic compound, and we dissolve it in water, we will get a clear blue solution. So the mixture on the right there shows dissolved copper 2 sulfate. So notice that the water is still clear. It's just that it's got that bright blue color from the copper 2 sulfate that's dissolved in there. Okay, as I mentioned earlier, while we deal mostly with aqueous solutions, solutions don't have to be a solid dissolved in liquid. As you can see here, there's a bunch of different examples of, for example, a gas-gas solution, a gas in a liquid, or solid in a solid. There's different examples out there. Okay, so how does water work as a solvent? I mentioned that we're going to spend a good chunk of this chapter talking about water or aqueous solutions, where water is the solvent. How does water dissolve things? It comes back to water being a very polar molecule. If you go back to chapter 5, I think we talk about how the electronegativity of the oxygen on your water molecule and its connection to a hydrogen, which is a very small atom, allows for hydrogen bonding, right? So that very electronegative oxygen is able to kind of pull away hydrogen's lone electron and make it very electropositive. And so you have hydrogen bonding between the very positive hydrogen on one molecule with the very negative oxygen on another molecule. Okay, and this is a very strong polar interaction. Well, the strength of this polarity allows water to dissolve a bunch of other substances, other things that are also polar. Okay, now that similarity of intermolecular forces is very important. Okay, water can only dissolve polar things. It will not mix with things that have London dispersion forces as their main intermolecular forces. Okay, that things that are nonpolar will not like to mix with water. They would prefer to hang out with themselves. Okay, so for example, in test tube A over here on the left, we have a mixture of water and carbon tetrachloride. Now, carbon tetrachloride, if you draw that molecule out, you'll see it's a nonpolar molecule. The carbon has 4 chlorines attached to it. There's no lone pairs on the carbon. It's, perfectly symmetrical, right? And so as a nonpolar molecule, it does not mix with water. We say that the two liquids are immiscible, all right? They don't mix. And so they form what's called a biphasic system. There are 2 layers in the test tube on the left there, okay, where water floats on top of carbon tetrachloride. Water is less dense than carbon tetrachloride. That's why it's on top, in case you're wondering. Okay, but in test tubes B and C, we have the same biphasic system, but we've added 2 different solutes. So in test tube B, we've added iodine. All right, now iodine is a nonpolar molecule. Notice that the dark purple-ish iodine dissolves only in the nonpolar carbon tetrachloride. None of it goes into the polar water. Okay, that's because since iodine only is nonpolar and only has London dispersion forces, it will only interact with the molecules of carbon tetrachloride and therefore dissolve in them. Okay, it will not mix with the water. And so, yeah, that's why that dark purple color of iodine is only in the bottom layer. Now look at test tube C. Here we've taken nickel 2 nitrate, which is an ionic compound. And you'll notice that this bright green salt dissolves only in the water layer. It does not go into the carbon tetrachloride layer. Okay. Now, the reason for this is, again, ionic compounds you could consider an ionic compound to be very, very, very polar, right? It's like ions are so polar to the point that they have separate charges, not just partial charges. And so an ionic compound like nickel 2 nitrate will dissolve in water, and we'll see how in a few slides. But again, it will dissolve only in the water and not in the nonpolar carbon tetrachloride. So we call this this phenomenon where a solute will only dissolve in the type of solvent that has similar intermolecular forces. You'll hear that described with the phrase like dissolves like. So only a polar solute will dissolve in a polar solvent like water. Nonpolar solutes will dissolve only in nonpolar solvents. Okay, and that's that. You won't have a polar solute dissolve in a nonpolar solvent. They'll be immiscible. They just won't mix, right? They'll form a heterogeneous mixture. Okay, so I think like oil and vinegar dressing is a good example of this. That's for a liquid solution, but your oil is nonpolar. Your vinegar, which is aqueous, is polar, and the two don't mix. And so if you look at oil and vinegar dressing, you'll see the globules of olive oil floating around in your dressing. They won't dissolve in the vinegar. So yeah, that's something to keep in mind when you're trying to decide if something will dissolve or not. Ask yourself, what type of intermolecular forces does it have? Is this molecule polar or nonpolar? Now, how do ionic compounds and other polar things dissolve in water? What happens when something dissolves, so to speak? Well, let's look at our solid first and ask ourselves how that, becomes an aqueous solution. So think back to a solid ionic compound. Now, if you go back to chapter 5 where we started talking about ionic compounds, you'll remember that our ions are positively and negatively charged, and they form this big crystal lattice where you have alternating positive and negatively charged ions, right? So we have this huge network where every negative ion is surrounded by positive ions and vice versa, okay? And so when you look at a salt crystal, that's kind of what that looks like zoomed in. Now, because of this setup, because of this network, only the outermost ions are capable of interacting with nearby water molecules. But they do interact. Remember, your negative ions are attracted to your partially positive hydrogens on your water. Likewise, your positive ions are attracted to your partially negative oxygens. Okay? So what happens then is these water molecules kind of peel off these ions bit by bit and surround them. Okay, so your sodium ion here, which is positive, is surrounded by water molecules with the oxygens facing that positive sodium. Okay, likewise, your chloride ions are surrounded by water molecules with the partially positive hydrogens facing that negative chloride ion. Okay, so now these ions are no longer trapped together in this crystal lattice. They are separate and free, and so we don't actually see them, because when we're looking at the solution, instead of seeing this big clump of ions together as a solid salt, we see the water molecules that are surrounding each of these individual ions. This is why the salt, or whatever your solute is, appears to quote-unquote disappear as it dissolves. It doesn't go anywhere. It's just being made invisible because it's surrounded by water molecules. Okay, a quick note here about how to represent this in an equation. We start off with sodium chloride as a solid, and when it dissolves, we have our separate sodium ions, which we write as aqueous, and separate chloride ions, which are also aqueous. All right. By representing these separate ions, we are getting into what's called an ionic equation. I'm going to spend a good chunk of this chapter talking about that. And if you look at your lab report for the soluble and insoluble salts lab, you'll notice that there's a section that deals with these ionic equations as well. Okay, so we'll get into more detail on how to split up these ionic compounds into their ions and write them in ionic equations. Okay, so I'll get into that in a little bit. Okay, but something to keep in mind there. All right, so again, this isn't limited just to ionic compounds. This is to anything that's polar. Anything that's polar and has a positive end and a negative end will interact with the negative and positive ends of water molecules and form solutions that way. So, for example, here's methanol, which is a type of alcohol. It's an organic compound that has an oxygen and a hydrogen on it, and therefore is capable of hydrogen bonding. Well, the methanol molecules hydrogen bond with each other, as shown in this picture on the left, just as water molecules hydrogen bond with each other. So it makes sense then that methanol can dissolve in water. You just have these hydrogen bonding interactions between methanol molecules and water molecules. Okay. So, yeah, and again, like dissolves like. So if you're looking at a nonpolar molecule, it will only dissolve in nonpolar solvents, not water. Okay, so you need something nonpolar, like something greasy, so to speak, like hexane or some sort of oil to dissolve these nonpolar molecules. Okay, so that, by the way, is you could actually see this for yourself if you want to try this at home. Let's say if you're you get grease on your hands and you want to try and wash it off. If you just run water over it, your hands will still feel greasy, right? That's why you need soap. Soap basically is kind of both polar and nonpolar, and that's how it's able to pull off greasy things into polar water. But if you want to see this effect of like dissolves like, try using something non-polar to kind of wash stuff off your hands. So, for example, if you have, let's say, something really greasy, like engine grease or something, like you're working on a car and your hands get really dirty, they would probably wash off with just some like vegetable oil, okay, or something like that, or some hexane. Of course, at that point, then you have vegetable oils on your hands, but that will probably wash off a little bit easier with soap, I guess. Anyway, so that's something to keep in mind with how to dissolve non-polar things. You can't just wash them off with water, which is polar. All right, here's some examples of some mixtures, and see if you can identify which of these are the solute and which of these are the solvent. Okay, remember, the solute makes up the smaller portion of the mixture, and the solvent makes up the majority. Okay, so I'm going to put up the answers in the next slide so you can have a look. Okay, there you go. So you can see in that first one, sugar is only 2 grams compared to 100 grams of water. Water has a density of 1 gram per milliliter, so 100 milliliters is the same as 100 grams. Here we have 60 milliliters of ethanol and 30 milliliters of methanol, so the solute is methanol. Over here we have 55 milliliters of water, which is equivalent to 55 grams, and only 1.5 grams of sodium chloride, so that must be the solute. And of course, in air we have 4 times as much nitrogen as oxygen, so the solute must be oxygen. Okay, and by the way, we've only identified the solute in each of these examples. Since each of these mixtures has only 2 things, the thing that's not the solute is the solvent, essentially. Okay, if you look at lithium chloride, that's an ionic compound, and it will dissolve in water. How does it dissolve in water? What part of water do the lithium ions get attracted to? What part of water do the chloride ions get attracted to? Okay, so this one hopefully should be pretty straightforward. Your lithium ions are positively charged, right? So they'll get attracted to the partially negative oxygens. Likewise, your negative chloride ions get attracted to the partially positive hydrogens. Okay, this is a good test for like dissolves like. So ask yourself, which of these will dissolve in water? So remember, due to like that phrase, like dissolves like, water is polar. Look for other polar things. Okay, and remember, ionic compounds in this context also count as polar. Okay, so hopefully you figured out that sodium sulfate, which is ionic, will dissolve in water, as will HCl. Hydrogen and chlorine have vastly different electron activities. and so this polar molecule will dissolve in water. Okay, gasoline and iodine, which are nonpolar molecules, will not dissolve. Okay, I briefly mentioned earlier when we looked at how something like an ionic compound like sodium chloride dissolves in water, I mentioned that it involves the splitting up of the ions from your crystal lattice, from the crystal of sodium chloride. Okay, this ability of a compound to kind of dissolve as ions is, we call that those types of ions electrolytes. Now, you've probably heard of the term electrolyte, probably from a Gatorade commercial, right? Or the movie Idiocracy. But basically, you may have heard that phrase before, and you're just thinking like, well, what are electrolytes, right? Why are they called that? They're called electrolytes. Well, first of all, here in this context, an electrolyte is just essentially a salt. It's an ionic compound that's dissolved in water, right? Now, why is it called an electrolyte? Well, electrolytes are things that help a solution conduct electricity. Okay, the reason for this is that your ions are charged particles. If you can convince them to travel in a straight line or travel in one direction, that's basically an electrical current. Okay, so having these charged particles available in a solution makes the solution a good conductor of electricity. Okay, and that's why we call them electrolytes. So, how do they work? Well, we have three different camps when it comes to electrolytes, three different categories. Strong electrolytes are compounds that completely dissociate in water. That means they completely break apart into positive and negative ions. So this includes things like soluble, ionic compounds. They will completely break up into their ions. Strong acids and strong bases also will act as strong electrolytes, by the way. Okay, so you can see here we have sodium chloride, and as we saw earlier, it splits up into sodium ions that are aqueous and chloride ions, which are aqueous. Now, I want you to pay attention to the arrow over here. This arrow is, well, a regular arrow, but what it tells us is that this reaction happens only in one direction. Our sodium chloride solid will completely break apart into its aqueous ions. Now, if a strong electrolyte completely breaks apart into its ions, a weak electrolyte only partially breaks apart into its ions. So we have a partial dissociation when a weak electrolyte dissolves in water. Now, what I mean by this is that most of your molecule, your solute here, will stay intact as, well, complete solute molecules. Only a few of them will break apart into those ions that we see. Okay, so we have the same sort of quote-unquote reactants and products here in our equation. Okay, and we still want to show that our solute molecules are breaking apart into these ions, but we want to show that this only happens partially. So to do that, we use a reversible arrow. We'll talk about reversible reactions a little bit in more detail next chapter, but for now, what this means is that while some of these molecules are breaking apart, simultaneously, some of those ions are reforming those original molecules. Okay. By the way, I've drawn this out with two double-headed arrows. If you were drawing this by hand, most people typically draw these reversible arrows like this when drawing by hand. Okay, so that's kind of what a reversible arrow looks like. Okay, and again, we'll talk more about that in the next chapter. So again, with the difference between a strong and a weak electrolyte, when written on paper, is just this arrow in between your undissolved solute and the particles it splits up into, the ions it splits up into. Okay? In the case of a strong electrolyte, this is just a one-way arrow. In the case of a weak electrolyte, it's a reversible arrow. And then, of course, we have non-electrolytes. A non-electrolyte is called that because it will dissolve in water but will not split up into any ions. The molecules are capable of dissolving in water because they're polar, or they have hydrogen bonding, but they stay intact as molecules. They do not form ions. So this is a good example of this is with most sugars. Okay, so sugar, any sugar that you look at has alcohol groups on it, OH groups, and therefore is capable of hydrogen bonding with water, and that's why sugars will dissolve in water. Same thing with any alcohol, for example. So like methanol is shown here in this picture, and over here we have sucrose, which is a type of sugar. When these dissolve in water, they stay the same molecules. So the only thing that's changing here is you go from a solid becoming aqueous. But that's it. Notice that the molecule itself is unchanged. It's still neutral. And therefore, there's nothing with a charge that's capable of conducting electricity. So, let's show how to write out some of these equations representing strong and weak electrolytes. So in this study check, we have two examples of strong electrolytes. And again, you can tell that they're strong electrolytes because we have an arrow here, okay? And we're starting off with ionic compounds. Plus the question tells us these are strong electrolytes, so we'll go with that. This is a good practice for later on in this chapter when we do get into ionic compounds, into ionic equations, because it's very important when we look at strong electrolytes to think about what ions they split up into. Okay, so look at this first example here. Here we have calcium chloride. We're going to get the cation from this, which is a calcium ion, and the anion from this, which is a chloride ion. But the thing to pay attention to is that 2 down there. Do the 2 chloride ions that come out of our calcium chloride stick together? And the answer is no, they don't. They are separate and free. So where that 2 goes is very important. Okay? So you might be tempted to write out your Cl2 and just leave it the way it is in your formula for calcium chloride, but by putting that 2 down there, you're implying that the chlorines are stuck together like some sort of polyatomic ion, which they aren't. Chloride is just a monoatomic. So to show that, we have to put the 2 in front as a coefficient. So the correct answer for this question is C. All right. Now, for this question here, we have potassium phosphate. So what's your cation and what is your anion? Your cation is potassium, which has the formula K+. Your anion is the polyatomic ion phosphate, PO4, with 3- charge. This, by the way, hopefully if you've started to get familiar with some of your polyatomic ions, but if not, it might be useful to have a list of them, a table of them in front of you when you try these problems out. And I do recommend gradually becoming more and more familiar with them. But anyway, so you write out the K+ and the PO4 3-, and then you worry about balancing this. So your 3 potassium ions here are not stuck together, and we have to put that 3 in front. Okay, it turns out the answer to this question is A. Here, I'll put the answers up so you can see you don't get distracted by the wrong answers there. Phosphate, of course, stays phosphate. It's PO4 with a 3- charge. You do not have the phosphorus and the oxygen split up because they are covalently bonded to each other. Okay, it's only the ionic bonds that are kind of broken up as we dissolve our potassium phosphate. So we split into our positive potassium ions and our negative phosphate ions, which are polyatomics and have the phosphorus and oxygen stuck together covalently. Okay, so watch out for that. That's a common tripping point for a lot of students. Okay, so again, we'll practice this some more when we get to ionic equations in this chapter. And you probably have already seen this, or will see this, if you do the lab on soluble and insoluble salts. Part A of that lab involves writing out ionic equations and being able to figure out the cations and the anions, right? The cations, which are positive, and the anions, which are negative, from your ionic compound is very important. Okay, so here are some examples of of solutes dissolving to form solutions. Which of these represent a strong electrolyte? Okay. So remember, for a strong electrolyte, you need a lot of ions to be present. You need your solid your solute to completely dissociate into its ions. Okay, we can tell automatically there are no weak electrolytes here. These are all regular forward arrows. There's no reversible arrows that show a weak electrolyte. So out of these products, which ones show ions? Well, only option C, and that's your strong electrolyte. Okay, so let's practice writing out each of these equations. Now we have one example of each. We have potassium chromate, which is a strong electrolyte. So you're told it's completely dissociating into its ions, potassium ions and chromate ions. If it helps, I'll point out here that potassium, of course, it's in group 1. It has a +1 charge. Chromate is a polyatomic ion. It has the formula CrO4 with a -2 charge. Okay, so that's the formula of the chromate polyatomic ion, and it's going to stay intact that way in the product side of that equation. Okay. All right. Then we also have the partial dissociation of a weak electrolyte, phosphoric acid. Okay, phosphoric acid splits up into hydrogen ions because it's an acid. It gives off H+. We'll talk more about that in chapter 12. And of course, we'll get phosphate, which is PO4 with a 3- charge. Then finally, we have the dissolving of sugar. Okay, sugar, I will tell you right now, is a non-electrolyte. So think about how you would write out that equation. So feel free to pause this video and try this out. Okay, so hopefully you got these answers here. So remember, your potassium chromate splits up into K+ ions and chromate ions, CrO4 2-. And because it's a strong electrolyte, this is just a regular forward arrow. Now, since there's 2 potassium ions in this formula, you've got to put that 2 in front over here. Okay, you cannot leave that 2 down here as a subscript because your potassium ions are not a polyatomic ion. Okay, you leave the 4 as part of the CrO4 2- because the oxygens here are part of a polyatomic ion, chromate. Okay, with our phosphoric acid, it splits up into H+ ions. Okay, if you accidentally wrote this out as 3 H+ and PO4 with a 3- charge, that's okay. We'll let that go. Technically, the protons get plucked off one at a time. So your anion here is dihydrogen phosphate. Okay, that's the actual product of the dissociation of phosphoric acid. We'll talk more about this in chapter 12, and you'll understand why this happens. This is a common trend for polyprotic acids like phosphoric acids, where it gets more and more difficult to keep on plucking off these H+. So if you didn't get this quite right, that's okay. But the important thing here is to realize that you're going to have this reversible arrow. Okay, that shows that this is a weak electrolyte. Okay, again, this is something we'll talk more about in chapter 12, where this having a reversible arrow here instead of a regular arrow is the difference between a weak acid and a strong acid. And finally, we have our non-electrolyte. So we have the same reactant and product. The only difference is we have a solid on the left, aqueous on the right, but otherwise the formula is unchanged. Okay. By the way, the whole solid to aqueous is kind of universal for all of these. In all of these cases, we have a solid solute dissolving to make an aqueous solution. So, your species on the right hand of your equation are always aqueous. Okay, let's jump gears here a little bit and talk a little bit about the concentrations of electrolytes. For those of you, especially who are going to nursing and other health sciences fields, it is important to make up solutions, but you want to keep track of the amounts of electrolytes in your solutions, right? This can be kind of important. And you also want to consider how to balance out the charges in your electrolyte solutions, right? So if you have any positive ions, they need to be balanced out by negative ions. But more importantly, the number of positive charges need to be balanced out by the number of negative charges, okay? I point this out because let's say you have calcium, which has whose ions have a 2+ charge. Well, you would need double the number of chloride ions because each chloride ion has only one negative charge. Okay, so in other words, your concentration of chloride would be double your concentration of calcium. Now, this can sometimes get a little confusing when you're thinking about making these solutions. So that's why we think in terms of equivalence. An equivalent refers to the amount of charges, not the amount of ions in your solution. Okay, so one equivalent is effectively 1 mole of electrical charges. Okay. And so typically we're going to look at solutions that describe, how many of these charged particles, how many charges do we have per liter of solution. Also, sometimes dealing with equivalents might be too many ions, too high a concentration. So to scale it down, we'll use milli, which remember from our metric prefixes, milli is 1,000th. So 1 milli equivalent, one equivalent is equal to 1,000 milli equivalents. Okay, so you'll often see concentrations expressed as milli equivalents per liter, for example. All right. So the key thing is realizing that you can then use these numbers to add up positive and like charges and have them counteract opposite charges. So for example, let's say you have a solution that's 29 milliequivalents per liter in chloride. You need to have the same number in positive ions, but it doesn't have to be the same ion. We could use something that's, let's say, 25 milliequivalents per liter of sodium ions and 4 milliequivalents per liter of potassium ions. Since those two numbers add up to 29, they will balance out the 29 milliequivalents per liter for our chloride, and we can make up our solution accordingly. Okay, but be wary, of course, though, that the charge of your ions will come into play here when determining your equivalence for 1 mole of that solution. Okay, so if you have 1 mole of sodium ions, it would give you 1 equivalent. But if you had 1 mole of calcium ions, that would be 2 equivalents because each calcium ion has a 2+ charge. So something to watch out for. Okay, so just whatever your charge is, just multiply that by that will correspond to your number of equivalents per mole. Okay, so in other words, how many moles you've got, multiply that by your charge, and that'll tell you the number of equivalents. Okay, so here's an example. Let's say we have a solution of calcium ions with a concentration of 8.8 milliequivalents per liters. Now, how many moles of calcium ion are present in 0.5 liters of blood with this level? Okay, so we're starting off with 0.5 liters. We want to get liters to cancel out and eventually wind up with moles of calcium ions. So we're told that we have 8.8 milliequivalents per liter. So if we multiply by 8.8 milliequivalents per liter, liters cancel out and we have milliequivalents, which we want to convert into equivalents. So we divide by 1,000 since there are 1,000 milliequivalents per equivalent. And so we wind up with 0.0044 equivalents of calcium, which is great. Well, we want to convert this to moles. Now, if you look at your calcium ions charge of 2+, that tells you that 1 mole of calcium ions has 2 equivalents. Okay, because remember that equivalents per mole is based on that charge, right? So there's 2 equivalents for every 1 mole of calcium. So if we divide by 2, okay, equivalence cancels out, and that tells us the number of moles we have, and we have 0.0022 moles of calcium ions, okay, which is half the number of equivalents. Okay, and of course we can do this backwards. If we started off with moles and we wanted to convert to equivalents, we would multiply by that charge. So if we had 0.022 moles of calcium and we multiply by 2, we would have 0.0044 equivalents of calcium. Okay, so let's say we want to balance out that calcium with chloride. What is the concentration in milliequivalents per liter? Well, it'll be the same as that of the calcium, right? It'll be 8.8 milliequivalents per liter as well. It's the same number. Okay. Now, do we have the same number of moles of chloride? And the answer is no, because the ratio of moles to equivalents is going to be different for chloride because it's only -1. Okay, so something to keep in mind there. That's why, again, we don't want to talk about moles here because then you've got to take into account those difference in charges. Okay, but if you deal with equivalents, you don't have to worry about that. Okay, so yeah, that's kind of typical for dealing with solutions like this, especially in health sciences, especially when you're trying to make, let's say, saline solutions or things that are isotonic with plasma. So something to keep in mind for those of you going into the health health sciences fields. Okay, let's try some practice problems that get us to practice this. Okay, so we have 1 mole of iron 3 plus. How many equivalents are there? Okay, so remember, to find out the answer to this, you've got to take the charge on your ion and multiply it by the number of moles, which in this case is 1. So your answer is 3 equivalents. Okay, take a second and try the next two before I show the answer. So feel free to pause this video if you need some time to think about it. Okay, so for the second one, we have 2.5 moles of sulfate. Okay, how many equivalents are there? So again, we're going to take our charge of 2 minus, but again, we're going to take the absolute value. It doesn't matter that it's a negative charge. So we're going to take that 2 from our 2 minus and multiply it by 2.5 moles. So that would give us 5 equivalents. Okay, so that's how you can figure it out. That charge of 2 over there tells us there's 2 equivalents for every mole of sulfate, and that's why we multiply by 2. Okay, and the last problem tells us that we have 34 milliequivalents of per liter of sodium ions. What must the concentration of the chloride be? Well, it's the same number, right? If we're using milliequivalents per liter, that's the nice thing about using equivalents. The numbers are, well, equivalent. So, okay. So I went over equivalents while we were talking about electrolytes, since that's kind of relevant for a lot of you going into the health fields. To be honest with you, we don't really talk too much about equivalents in terms of the curriculum for Chem 103. We're not really going to have that show up too much on the exam or the final, or the quiz or the final. So something to keep in mind. Okay, so don't stress too much about it. For those of you who are not going to health sciences and you're kind of struggling, well, what do we do with these equivalents thing? We won't really assess it too much in this course, but for those of you who are going to health sciences, I'm sure it's something that will come up in other classes. Okay, so let's switch gears again. You'll find that this chapter tends to do that. It breaks up into lots of little small topics. But let's talk about quantifying how much solute a solution can hold. Okay, we term this solubility. This is the maximum amount of solute that we can dissolve in a set amount of solvent. Okay, now this is temperature dependent. Basically, you'll see that solubility will change at different temperatures. So oftentimes when these solubility values are given, they also mention what temperature that solubility applies, at what temperature it applies to. It's typically expressed in grams of solute for every 100 grams of water in the case of aqueous solutions. Okay, so now what a solubility value will tell us is the point at which a solution will become saturated. Okay, so what do I mean by saturated? Well, an unsaturated solution is one that can dissolve more solute. We haven't hit that maximum, that limit that stops more solute dissolving. Okay, so there's room in the solvent for more solute to go into. And you can tell this because your solution, well, looks like solvent. There's, all of your solute dissolves, basically. Compare that to a saturated solution. Now, in a saturated solution, you have met the maximum amount of solute that can dissolve. So at this point, you are adding extra solute. So you can tell that a solution is saturated when there is undissolved solute left at the bottom of the solution. It's not going to dissolve. What happens now is that an equilibrium sets up where your solute that's undissolved will start dissolving. At the same time, some of your dissolved solute will start crashing out. Okay, so there's a bit of an equilibrium going on. You'll have like leftover solute, and some of it's going to solution, but at the same time it's kicking out some solute that's already dissolved and causes it to crystallize again. Okay. So that's basically how you identify a saturated versus an unsaturated solution, right? Just by appearance. Okay, so if you see salt, just readily dissolving, readily disappearing when you put it in water, that should tell you that that solution is unsaturated, right? And likewise, if sugar is added to a cup of water, but it does not dissolve, it just settles to the bottom, well, what does that tell you? Well, it tells you that the sugar solution has the maximum amount of sugar already, and therefore that is a saturated solution. Okay, so keep that in mind from a visual standpoint. If you're looking at a solution and you're trying to decide, is this saturated or unsaturated? That's how you tell the difference. Okay, so the word saturated just means full. It's got the maximum amount of solute it can take. But let's bring math into this, right? Let's bring numbers into this. What do these solubility values tell us? They tell us that for 100 grams of water, how many grams of solute do we need to saturate a solution? And by scaling our amounts up or down to compare to these solubility values, if our amount of solute is less than our solubility value, well, that tells us then that we have an unsaturated solution. If our amount of solute is more than the solubility value, then we have a saturated solution. Okay, so that's how we're going to tell the difference. So let's have a look at this particular solution. We're told that at 40 degrees Celsius, the solubility of potassium bromide is 80 grams for every 100 grams of water. Okay, now please note all of the problems we're provided are also at 40 degrees Celsius. So you actually don't have to worry about the temperature. The only reason they gave you the temperature is to show that temperature is not a factor here. It's staying constant. Okay, so let's look at this first example. We have 60 grams of potassium bromide, and we add it to 100 grams of water. Is this going to be a saturated solution or unsaturated? Will all 60 grams dissolve? And the answer is yes, right? Since the solubility is 80 grams of water, 80 grams of potassium bromide for every 100 grams of water, well, 60 grams is less than 80, so all 60 grams will dissolve. Okay, so this will be an unsaturated solution. Now, let's try the second problem out. Here we have 200 grams of KBr added to 200 grams of water. So now we're not comparing apples to apples, right? We have 200 grams of KBr in 200 grams of water, but our solubility value shows the grams of KBr in 100 grams of water. So we need to scale this down so that we have 100 grams of water instead. Okay? So what we're going to do then is we're going to essentially divide by 2. So we're going to take 200 grams of KBr, multiply by 100 grams of water, and divide by 200 grams of water, and that tells us how much KBr would be in 100 grams. Okay? So in this case, it happens to be, we're dividing by 2. We want to see how much would dissolve in half this amount of water. That would be 100 grams of KBr. Well, 100 is greater than 80. So that tells us that is a saturated solution. Okay? Likewise, for the last one, you're going to figure out it's unsaturated. So you have 25 grams of KBr and 50 grams of water. So if we double those 50 grams to 100 grams, our 25 grams of KBr also doubles to 50. Well, 50 is less than 80, and that's why it's an unsaturated solution. Okay, so if you're having trouble seeing this, okay, for those of you who like writing out in ratios, you could set it as 25 is for every 50 grams of water, right? For KBr, right? And we want to scale this up to figure out how many grams of KBr do we have in 100 grams of water. Oops, that should have been water, not H2O, not KBr. There we go, sorry. 100 grams of water. There we go. Okay, so we want to find this number by itself, so we're going to just multiply this up here. Okay, so 25 times 100 divided by 50 will tell us how much KBr would be dissolved in 100 grams of water if we scaled up this ratio. Okay, and when we do that, we get 50 grams of KBr. And we compare this number with this number. Well, 50 is less than 80, and that's why this is an unsaturated solution. Okay, so that's effectively what we did over here in the second problem as well. We didn't really have to do it for this first one because this was already at 100 grams of water. Okay, but that's effectively what you're doing. You want to scale this up or down accordingly so that we see how much would be dissolved in 100 grams of water, and then we compare it to the value that the question gives us. Okay, now I mentioned that the question has to provide the temperature so that you know that the temperature is not changing. Now, why is that so important? Well, I mentioned that solubility is temperature dependent. The solubility value will change with temperature. Okay, in fact, we're going to see this in the lab on soluble and insoluble salts. We actually went up plotting a solubility curve for potassium nitrate in that lab. So you're going to see that the amount of potassium nitrate that you can dissolve will increase as the temperature increases. And this is typically true for for pretty much almost every solid solute. Solid solutes tend to dissolve better as your temperature increases. Now, the rate at which that changes is different for different solutes. And so you can see that all of these graphs have, all of these lines have different slopes. But the important thing is to realize that all of these slopes are positive slopes. As our temperature increases, our solubility value also increases. Okay, so that's just something to keep in mind for solids. Okay, I think the reason for this is that as you increase the temperature, you have more interaction between your solute and solvent molecules, and that allows your solute molecules to sort of get plucked out of that crystal structure, right, a little bit easier. Now, with gases, on the other hand, we see the opposite trend. Gases actually get less soluble as the temperature increases. Okay, so again, I think this has to do with kinetic energy as well. I think gases are well, this is going to get into a discussion on entropy, which is a topic that's beyond the scope of this class. But basically, gases like to have a little bit more chaos, a little bit more freedom, I guess. So when you heat up a gas or a solution containing gases, the gas molecules prefer to be in the gas state rather than tied down with the solvent in your solution. Okay, so that's why typically your solubility of gases tends to decrease with temperature. If you ever want to test this out in real life for both solids or for gases, well, with solids, you could probably see that it's easier to dissolve sugar in hot tea than in cold tea, right? If you try to dissolve, take like hot water and cold water and try and dissolve sugar or salt in it, and you'll see that it's easier to dissolve it in the hot water than the cold water. But look at a carbonated beverage. So let's say you have a bottle of Coke, right? And you leave it out. You don't put it in the fridge, right? Or heck, put it on top of the fridge where it warms up a lot faster. You'll notice that that bottle of Coke will go flat a lot quicker than a bottle that is left in the fridge. Okay, so that's one of the reasons why we like to refrigerate carbonated beverages, to help keep them carbonated and stop them going flat. Okay, while I'm using that example, another thing we want to talk about is Henry's law, and I'll get into that in another slide. Okay, so here's a couple of applications of the solubility of gases in liquids. I kind of already talked about heating up a carbonated beverage. So basically, your carbon dioxide starts leaving solution. into the gas phase as you warm up the bottle. Okay, so the exploding part here is because the gaseous carbon dioxide is still trapped in the bottle, and that gas pressure, keeps on increasing, and that might cause the bottle to explode. Okay. Why do fish die in water that is too warm? I don't know if you've noticed, but in unusually hot summers, you might notice, that if you live by a lake or a pond, you might notice that there are more dead fish floating in the water when when the temperature starts rising to a higher than average. Okay, this is one of the concerns with climate change, right? If you're in a region that experiences rising average temperatures, I know like with global warming that happens globally, but in terms of specific climates, if you're in a place that has local temperatures also climbing up on average, does that why is that such a big concern for fish populations? Well, you'll find that local fish populations start dying off. Okay, you start decreasing the amount of living fish. Okay, and the reason for this is that fish breathe because of dissolved oxygen in the water, right? Well, and that's what their gills do. It kind of separates out, it filters out dissolved oxygen in the water. Well, if you have less oxygen that's dissolved in the water because the temperature is rising, your fish start essentially, asphyxiating. They essentially start suffocating because of a lack of oxygen in the water. Okay, so I mentioned Henry's law earlier when we think about carbonated beverages and gases under pressure in carbonated beverages. Basically, Henry's law is the relationship between the pressure of a gas and the concentration of that dissolved gas in a solvent. Okay, so again, a good example of this is with a carbonated beverage. Think about when you open up a can or bottle of carbonated beverage. What's the first thing you hear? You hear that hissing noise. Now, that hissing noise you hear is due to carbon dioxide escaping, because when the beverage is bottled or canned, they actually inject a higher pressure of carbon dioxide into the can to keep it, or the bottle, to keep the beverage carbonated. So usually that pressure is somewhere around like 6 atmospheres, so 6 times atmospheric pressure. Okay, so when you open up the can or bottle, that hissing noise you hear is carbon dioxide escaping because it wants to equalize the pressure with the atmospheric pressure, which is usually somewhere around 1 atmosphere. Well, what's the next thing you noticed when you've opened your can after that hissing noise? Well, this is probably a little bit easier to see in a bottle rather than in a can, which is kind of solid. But if you take a bottle of Coke and you open up the top, right, and you hear that hissing noise, the next thing you see a whole bunch of bubbles appearing, right? Now, why is that? Okay, because according to Henry's law, when that pressure drops down from 6 atmospheres down to 1 atmosphere, the solubility of the gas, of the dissolved carbon dioxide, decreases. Well, where does that gas go? It leaves as gas bubbles, and those are the bubbles that you see. All right, so that's why when you first open up a bottle of Coke, that's the reason why you see those bubbles appearing after you hear that hissing noise. Okay, with Henry's law, go back here. With Henry's law, we can do calculations relating pressure and concentration. There's usually a constant that ties the two together. We're not really going to do that in this class, but for any of you who are going on to Chem 111 and 112, those are calculations you would be capable of doing. Okay, so earlier when we talked about strong electrolytes, I mentioned that ionic compounds will dissolve in water because like dissolves like. Ionic compounds dissolve in water because those ions interact with the polar water. And ionic compounds are strong electrolytes. They completely dissociate into their ions, which is great. I neglected to tell you that you need a water-soluble ionic compound to dissolve in water, okay, for this effect to be observed. Okay, now what determines if a compound, an ionic compound, is going to be water soluble or not? It comes down to the strength of those ionic interactions in that crystal lattice. Do your ions prefer to be a solid, as like, a crystal in that crystal lattice, or do they prefer to be surrounded by water molecules and dissolved in water? Okay, for a lot of ionic compounds, the latter is the case. Okay, it's actually just energetically favorable for them to be dissolved in water. But for a bunch of ionic compounds, they prefer to be solid crystals. They prefer to clump together and form that crystal lattice. And we call these insoluble salts or insoluble ionic compounds. Now, you can obviously observe this in lab. You can see, like, okay, this salt does not dissolve in water. But how do you predict if an ionic compound is going to dissolve in water or not? Well, thankfully, at some point, scientists just cataloged how many, they just noticed which ions formed compounds that prefer to be soluble and which ones prefer to be insoluble. And they noticed some patterns, and we call these solubility rules. Now, these solubility rules are written out in different forms, but the key thing to take away is to know which salts have ions that will encourage solubility. And I would say you could try memorizing all these rules, but to be honest with you, as far as this class goes, you don't have to memorize them all. What's more important for the lab on soluble and insoluble salts is being able to read a table like this and having it in front of you. But for a quiz or exam where it might be helpful to predict whether you're going to have a soluble or insoluble salt, you don't have to actually have to memorize everything. You just need to memorize kind of these first two lines here, because there are no exceptions for those. Okay, so typically group 1 metals like lithium, sodium, potassium, rubidium, cesium, and ammonium salts all tend to be water soluble. Okay, it doesn't matter what the anion is. If your salt has that one of these as its cation, it will dissolve in water. Okay. Likewise, the anions nitrate and acetate will also always be soluble. So they're salts. It doesn't matter what the cation is. That salt that contains nitrate or acetate will dissolve in water. Okay. So if you remember that, you will be able to get by on any quiz or exam as far as Chem 103 goes. Okay. Now, of course, there are exceptions out there for other salts that aren't covered by those ions. So, for example, typically chloride, bromide, and iodide salts tend to dissolve in water. There are some exceptions, though, like silver chloride or lead 2 iodide, or etc. Any combination of these ions with your halogens will make for an insoluble salt. Sulfate's also kind of pretty common like that. It's pretty soluble like that. Most sulfate salts are water soluble, but again, there are some exceptions. Barium sulfate, lead 2 sulfate, calcium sulfate, strontium sulfate, mercury sulfate, those will not dissolve in water. Now, of course, there are salts that have ions that we haven't covered here. Typically, most other ionic compounds that most ionic compounds you come across will include some of these ions, but if there are any that don't cover these ions, you can kind of assume that they're going to be insoluble. Okay, so typically things like phosphates or carbonates, ions like that tend to be insoluble. Okay, unless of course they're paired up with the group 1 metals or ammonium. Okay, so here are some examples of insoluble salts, and you can see that they clump around as solids in our mixture. Okay, now this is going to be interesting for double replacement reactions that involve a precipitate. So you can make these insoluble salts by pairing up ions from reactants that are completely soluble. Okay, so I'm going to show you that in a little bit. But again, these are what those precipitates will look like. They're just solids that crash out of solution and turn the solution cloudy. Okay, so that's how you can quickly identify the presence of an insoluble salt that's formed. Okay. Yeah. So and again, there's lots of applications for these. So so you can see here for doing like a colonoscopy or just to enhance X-rays, you can use something like barium sulfate, which will not dissolve in water. It'll show up as a solid, and more importantly, as a solid, it blocks the X-rays. So it will make the thing holding it, in this case the digestive tract, show up as a solid. Okay, so let's practice using our solubility rules. Okay, so look at these 4 compounds here, and then go back a couple of slides and ask yourself, do those rules apply to this compound? Is this going to be soluble or insoluble? Okay. All right. So again, if you've come back from pausing this video, let's go through these answers. Okay, so if we look at cadmium sulfide here, okay, a quick giveaway is that we don't see any of the ions that are mentioned on in that table I had a couple of slides ago. Depending on the solubility table or solubility rules table that you're following, sometimes they mention that sulfides tend to be insoluble. So a lot of these sulfides are not soluble in water unless they're paired up with a group 1 metal or ammonium, right? So like something like sodium sulfide or ammonium sulfide would be soluble, but cadmium sulfide would not. So that's going to be insoluble. Okay. Next, we have sodium sulfate. Immediately, as soon as you see that sodium ion, you should immediately say, oh, that's going to be soluble. Okay, that's a dead giveaway. As soon as you see that group 1 metal sodium, you automatically know it's going to dissolve in water. Okay, sulfate salts are typically soluble as well, but that really, you don't even need to know that to solve this problem. Right? As soon as you see that sodium, you know the answer. All right, lead 2 iodide. Now you look at this and you say, oh, there's an iodide ion in there. If I go back to those rules, it tells me that iodide salts are typically soluble. Okay, so you might be tempted to immediately write soluble, but look at the exceptions for iodide, and you'll see that lead iodide is one of those exceptions. Okay, so you've got lead 2 plus ions paired up with our iodide, and that's what makes this insoluble. And then finally, we have nickel 2 nitrate. And again, as soon as you see that nitrate in that formula, that should immediately pop out like, oh, this is a soluble salt. Anything with nitrate is going to be soluble. Okay, it doesn't matter what the cation is. As soon as you see nitrate as your anion, boom, you know the answer is going to be soluble. Okay. So that brings us to writing out ionic equations and net ionic equations as a next follow-up to ionic equations. So I kind of talked to you about this quite a bit in earlier in this chapter when we talked about electrolytes. Okay, so it's very important to realize that water-soluble ionic compounds are strong electrolytes. They are going to split up into their cations and their anions. You're going to get 2 pieces out of every ionic compound, okay, that is aqueous, and we're going to represent that in our ionic equation. Okay, and again, I kind of walk you through this in the video for our for the lab on soluble and insoluble salts as well. So if you haven't already done so, please watch that video too. But I'm going to explain it again here. So I think seeing it twice probably will help out. So let's look at an example of a double replacement reaction that involves a precipitate. So we can see exactly how these ionic and net ionic equations come into play. All right, so let's look at an example here for a reaction between lead 2 nitrate and potassium sulfate. All right, these are both going to be water-soluble salts. These will form aqueous solutions. Lead 2 nitrate, of course, has nitrate, so we know that's going to dissolve in water and form an aqueous solution. Potassium sulfate has potassium. We know that potassium salts are also going to dissolve in water. Okay. Now, this is a double replacement reaction. So what does that entail? Well, your cation for one reactant will pair up with the anion for the other, and likewise the cation of the other reactant will pair up with the anion of the first. So we do this in the lab, but this is a good practice for double replacement reactions in general. Split up your salts into their respective ions. So lead 2 nitrate splits up into lead 2 plus ions and nitrate ions, which are NO3 with a -1 charge. Okay, this is the formula of nitrate. Notice I do not put the parentheses and the 2 over there, because that's not the formula of nitrate. I need that 2 over there because we need 2 of those negatively charged nitrates to balance out the 2 plus charge in lead. But that parentheses 2 is not part of the formula of nitrate. Again, this is why I usually recommend, it's a good practice to start memorizing your formulas of polyatomic ions. Okay, again, you can get by without memorizing them, but this makes life a lot easier when it comes to writing out these ionic and net ionic equations. Okay, let's look at potassium sulfate. Again, it's split up into potassium ions, which have the formula K with a +1 charge, because potassium's in group 1. And then we have sulfate, which is a polyatomic ion with the formula SO4 with a 2- charge. Again, this imbalance of charge, the fact that potassium only has a +1 charge and sulfate's a 2- charge, that's why we have that 2 next to the potassium. But please keep in mind that 2 is not part of the formula of potassium. Okay, potassium is not a polyatomic ion where 2 potassium ions are stuck together. No, they are separate and free when that potassium sulfate dissolves in water. Okay, so we pair up those ions accordingly. So our potassium ions pair up with nitrate to form potassium nitrate. Our lead 2 plus ions pair up with sulfate 2- to form lead 2 sulfate. Okay, now don't forget to write out the formulas of those compounds. Well, they're going to be pretty straightforward because this plus charge is cancelled out by the negative charge of nitrate. So the formula of potassium nitrate is just KNO3. Likewise, the 2 plus charge and the 2- charge cancels out, and lead 2 sulfate has the formula PbSO4. Okay, so those formulas are relatively straightforward, though again, keep in mind it's not always so. Sometimes you may need to balance out charges to get the right formula. Okay, and again, the example I do on the lab report illustrates this. Now, looking at your two products, ask yourself, is one of these going to be insoluble? Okay. If you're told that this is a precipitation reaction, then you know one of these products has to be insoluble. It will not dissolve in water. So which of these two is that product? It might be easier to think of this backwards. Which of these two is not that product? Which of these two is definitely going to dissolve in water? Is definitely going to be soluble in water? Well, again, as soon as you see potassium or nitrate, you know that that's going to be a soluble salt, right? So you know that that cannot be your precipitate. Your precipitate must be PbSO4. Okay, that's your insoluble product. So how do we show this in a balanced equation, right? Now the balancing, of course, is important because you'll probably quickly notice that we don't have the same numbers of ions in both sides of the equation. Here, let me show you, let me write it out and you can see what I'm talking about. And this might make it apparent what I mean here, in terms of balancing. So let's write out our reactants, right? We have PbNO3, lead 2 nitrate, okay? Now this, of course, as I pointed out, as a nitrate salt, is going to be aqueous. So I'm just going to write that state symbol down here just to remind us that this is an aqueous salt. Okay, you may see this written to the right. Typically when the stuff's typed out, the state symbols are written to the right of the chemical instead of underneath. So you'll probably notice that quite a bit in most of these materials in our slides here, as well as the lab report. You'll notice that written out that way. But if you're writing this by hand and you want to save space instead of writing this all out on one line, feel free to write the state symbols underneath your chemicals. Okay, what's your other reactant? Well, we have potassium sulfate. That's K2SO4. Okay, now again, as a potassium salt, this is also going to be aqueous. Okay, and of course, we've just seen that we have these two products. We have our PbSO4 and we have our potassium nitrate. But don't forget, we want to put down state symbols for these as well. So what state symbols are going to go underneath these? Well, we just saw that lead 2 sulfate is insoluble, which means it is a solid. It does not dissolve in water. We see this as a cloudy yellow solid when we do this reaction. So if you haven't seen this reaction before, typically you start off with two clear colorless solutions, and when you mix them together, all of a sudden they turn yellow and cloudy. Well, that yellow cloudiness is the lead 2 sulfate. The state symbol, of course, for our potassium nitrate is going to be aqueous. Okay, and so there's all of our chemicals with our state symbols, but you'll quickly notice that this equation is not balanced, and this is very important if we're going to move on with this problem. Okay, so notice that we have two nitrate ions over here. Okay, we have only one nitrate ion in lead 2 nitrate, so our first step might be to put a 2 here to help balance out our number of lead ions and nitrate ions. Okay, we have, two nitrates on both sides. We have one lead on both sides. So that's a good sign. But now notice that we have two potassium ions here because we have two potassium nitrates. Well, what about, oh, hey, this already has two potassium ions. We're already balanced. So all we had to do was to put this 2 here. Let's double check and make sure everything is balanced out. I've already talked about how there's one lead over here and one lead over here. So that's good. There are two nitrates in our lead 2 nitrate, and there's two nitrates because we've got two potassium nitrates. Okay? We have two potassium ions here, and we have two potassium ions in our two potassium nitrates. And then finally we have a sulfate ion, SO4 with a 2- charge, and again we have SO4 with a 2- charge as part of our lead sulfate. So this is a good balanced equation. Now let's try writing it out as an ionic equation. To write out an ionic equation, you take each of these ionic compounds and you split them up into their ions, kind of like how we've done here. Okay. Now the thing to watch out for is that again, you have to remember that your ions are separate and free. So any subscripts that are used to help balance out charges are put in the front of those ions. So here's what the ionic equation for this reaction looks like. So our lead 2 nitrate, okay, so our PbNO3 twice, gets split up into Pb2+ ions and our nitrate ions, which are NO3-. But because there's two nitrate ions, we put that 2 in front as a coefficient. Okay, again, like the three oxygens and the nitrogen are covalently bonded together, but those two nitrate ions aren't covalently bonded to each other. Okay, they're held together by ionic bonds, and so once this dissolves in water, that's why it splits up into two separate ions. Okay. Likewise, here we have K2SO4, our potassium sulfate. Well, the formula for potassium ion is K+, but since these two ions aren't stuck together as a polyatomic ion, this 2 comes up in front here to show that there's two potassium ions that are separate and free when our potassium sulfate dissolves in water. Our sulfate just stays SO4 2-, because that's the formula of sulfate. Those 4 oxygens are covalently bonded to that sulfur. Okay, and this is the formula for your sulfate ion. And there's only one of that sulfate ion, so we don't have to put any numbers out in front here. Now, notice I did that to our aqueous reactants. What about our lead 2 sulfate? That is a solid. Those ions do not separate out, so we just write out the formula the way it is. Okay, but of course our potassium nitrate is aqueous, so we split that up into K+ ions and nitrate ions. But since there's two potassium nitrates, we get double the numbers of those ions. We have 2 potassium ions and 2 nitrate ions. So again, this helps, you can check your work because this is still a balanced equation, right? We still have like 2 potassium ions on both sides, 2 nitrate ions on both sides. We have a sulfate and a lead as well on both sides of that arrow. Okay, obviously this is a very long equation because everything's split up here with the exception of that solid lead 2 sulfate. So I've kind of had to like split this up into 2 lines, but ordinarily you try and write this all in one line if you could. Okay, now notice that we have some repeats on both sides of this equation. Okay, there are 2 things that are written exactly the same way on the left-hand side of the equation and the right-hand side of that arrow. And that is our potassium and nitrate ions. We call these spectator ions. Spectator ions are ions that are repeated exactly the same way on both sides of the equation, which tells us that they aren't really doing anything, right? Our potassium ions that are aqueous are still potassium ions that are aqueous on the right-hand side of the equation. Our nitrate ions, which are nitrate aqueous on the left-hand side of the equation, are still aqueous nitrate ions on the right-hand side of the equation, okay? So they cancel each other out. Okay, if you're wondering where that word spectator comes in, think of it as kind of like the spectator at a sporting event, right? Spectators are present at the sporting event. They're part of that environment, but they're just there to observe. They don't actually play the sport. They don't do anything. So in the same way, our potassium and nitrate ions are there. They're present. They balance out charges and stuff, but they don't actually do anything. They aren't changed in the course of this chemical reaction. So when we write a net ionic equation, we just remove the spectator ions from our ionic equation and we just show what's left over. What's left over is the actual reaction. What is happening here? Well, our net ionic equation shows us that lead 2 plus ions that are aqueous combine with sulfate ions that are aqueous, and they combine into this PbSO4, this lead 2 sulfate, which is a solid, a precipitate. Okay, that's the effective change that is going on in the formation of this precipitate. Okay, and that's basically how you walk through a double replacement reaction, a precipitation reaction, and get to the ionic and net ionic equation. So just to recap everything, okay, when you have your regular equation, split everything up into its ions, anything that's aqueous into its ions. Okay, so if you want to figure out the products, you can just switch partners and determine their formulas, and then decide which of these is going to be my insoluble product. Okay, but then to write out the ionic equation, all you've got to do is split up those ions and write them out separately. In the net ionic equation, you want to just take out those spectator ions. Okay, so we just cancel them out on both sides, and what we have left behind is called the net ionic equation. Now, a little quick pro tip here for if you're trying to save some time on a quiz or exam. If you were told, what your precipitate's going to be, and you want to write the net ionic equation directly without having to go through the trouble of writing the ionic equation, the shortcut here is to realize that your precipitate is always the product in your net ionic equation. Okay, the quote-unquote reactants for this are the ions that make that precipitate. So if you're told that your precipitate's going to be lead 2 sulfate, PbSO4, well, you know that your lead ions and sulfate ions are going to be on the left-hand side of that equation, and they're going to make that precipitate, and that's your net ionic equation. Okay, your spectator ions don't matter. You could use anything for spectator ions. Here we used potassium sulfate, but if we had used sodium sulfate instead, this net ionic equation would still be the same. Okay, the sodium ions would be our spectator ions that cancel out on both sides, so we wouldn't see them in this net ionic equation. And again, they're spectator ions, so they don't actually do anything. They aren't really that important. Okay, so that's how you write out those equations. And again, if you want to see more practice on this, be sure to check out your lab report and watch the video I've made for that lab. We're now going to get to a very important subtopic here, and that's describing concentrations of solutions. A concentration tells us essentially the ratio of solute to solvent, or the ratio of solute to solution, and that gives us a feel for just how much solute we are dealing with. Okay, so now, there are different ways to describe concentration. Some of them are probably already familiar to you. You use them just in day-to-day life. For example, percentage by volume. That's, give you a silly example there. That's how we, that's the ABV that you see on beer, basically. So if you see, for example, like a can of Budweiser is 5% ABV, that just means alcohol by volume, and that's just 5% alcohol is all that means. So we're going to look at different ways that we can, we can describe or write out our concentration or define our concentration. And you'll see that there are times some of these might be more useful to us as chemists, particularly the one where we're going to define our amount of solute in moles. So probably the simplest one, which again you may have seen before, is just a percentage by mass. It's the mass of solute over the mass of solution times 100%. Okay, so this is written as mass percentage or sometimes just percentage m/m. That just reminds you that your solute's given in terms of mass, and your solvent is, or your solution is also given in terms of mass. Now, please note that the denominator of your fraction here is the mass of solution, which is the mass of your solute and your mass of your solvent combined. This is very important, and this is a common sticking point for a lot of students. This is not just the mass of solvent, okay? It's both solute and solvent together. Okay, so watch out for that, because you can bet that on your multiple choice quizzes and exams, one of the wrong answers will have just the mass of solvent swapped out in there. Okay, a quick note here about the percentage answer that you get. You can then treat that as a conversion factor. Just know it's the same thing as the grams of solute for every 100 grams of solution. Okay, so when we have our beer that's 5%, or well, I guess that's a volume, but let's say we had a salt solution that's 5%, solute by mass. Basically, that just means for every 100 grams of solution, we have 5 grams of solute, of our salt that was dissolved in it. Okay, so let's see an actual example here. So let's say we take 42 grams of water and add it to 8 grams of potassium chloride. Okay, now how do we get the percent concentration there? Well, again, the answer is kind of given to you. They tell you it's 16, but how did they arrive at that number? Well, what's our solute and what's our solvent here? Well, our solute's going to be our potassium chloride. That's definitely the smaller part of that mixture. So we take our 8 grams of potassium chloride and we divide by 50 grams of solution. So please note, we don't divide just by the 42 grams from water, but we take the total mass of solution, which is 42 and 8, or 50 grams of solution. Okay, so even though we've used 8 grams here for our solute, we still have to take into account that 8 grams that potassium chloride contributes to the overall solution. And then, of course, 8 divided by 50 times 100 is 16%, and that's where they get that number. So let's try some problems out involving that. What is the mass percent of sodium hydroxide in a solution prepared by dissolving 30 grams of sodium hydroxide in 120 grams of water? So feel free to pause this video if you want to try this out yourself. So our solute is our 30 grams of sodium hydroxide. Our solution is going to weigh 150 grams, right? We've got 30 grams of sodium hydroxide plus the 120 grams from water, and that's 150 grams combined. So our percentage here by mass is just going to be 30 divided by 150 times 100, which works out to 20%. All right, let's try one more. So go ahead and pause this video and see if you can solve this one. Okay, so we've got our 15 grams of sodium carbonate. Our water is 235 grams, but again, remember your solution is water and sodium carbonate together. So that's 250 grams total of solution. So 15 divided by 250 is 6%. Okay, so now we're going to get to that beer example I was talking about. Basically, when we do a percent by volume, it's kind of the same thing. It's just your volume of, it's just your amount of solute divided by amount of solution. The only difference here is instead of mass, we're going to use volume. Okay, so Now, in both the cases of mass and volume percentages, it actually doesn't matter what units we use for our mass or volume. We can use, for mass, we can use kilograms, we can use grams. If you really wanted to, you could even use non-metric units like ounces or pounds. Likewise, for percentage by volume, we can use milliliters, we can use liters, we could use non-metric units like ounces or gallons, I don't know, whatever other English units involve volume. But basically, the reason for this is that the units cancel out. As long as you use the same units for your solute and your solution, the percentage winds up being unitless, as it should be. Okay, so, but anyway, when I gave you that example of a beer being 5% ABV, that just means that there's 5 milliliters of alcohol for every 100 milliliters of beer. Okay, or you could scale it up. There's 5 liters of alcohol in 100 liters of beer, and so on. Okay, that's all that percentage by volume means. Okay, and of course, again, we can still use this as a conversion factor. It's the same thing as saying that, well, I kind of just said that. There's 5 milliliters of our alcohol for 100 milliliters of the solution, in this case beer. Okay, yeah, so you can calculate your percentage by volume just by taking your volume of solute, dividing by your volume of solution times 100. So we'll see some examples of that in a little bit. Now, the third percentage that you might come across is mass per volume percent, or percent m/v. Okay. Actually, I believe in the last lab that we do, you guys are going to do a titration. Don't worry about what that is. You'll find out in chapter 12. It's an analytical technique. But anyway, the m/v is actually the type of concentration you guys are going to figure out for a sample of vinegar. So you guys will actually get to practice a lab doing these types of calculations. But what are the m and what are the v in percent m/v? Well, it's just mass and volume, right? Now, since we're not dealing with the same quantity, now here we do have to define what units we use. So our mass has to be in grams, and our volume has to be in milliliters for this to work. Okay? But again, it's a percentage just like everything else. So you take your mass of solute and divide by the volume of solution. So I'm hoping everyone's kind of seeing the pattern here. All three of these percentages have been some amount of solute divided by some amount of solution times 100%. Just how we measure the amount is different in each of the examples, and is, the thing in parentheses helps you remember. So m/v is mass of solute over volume of solution. Okay, and of course times 100% because it's a percentage. And just like the others, of course, you can write it out as a conversion factor. So if you have something that is 5% m/v, that means there are 5 grams of solute for every 100 milliliters of solution. So let's try practicing writing out those conversion factors. Okay, so take a second, think about each of these, make a close note of the m/m or v/v or m/v, and make a note of how that'll affect your units in your conversion factors. Okay, so for each of these you should come up with 2 fractions, 2 conversion factors that you can use to help convert between your amount of solute or amount of solvent. So for the first one, we have 8.5 mass / mass, so that's 8.5 grams of sodium hydroxide for every 100 grams of solution, or vice versa, 100 grams of solution for every 8.5 grams of sodium hydroxide. Okay, so remember, all of your conversion factors, your second conversion factor is just going to be the inverse of the first. Okay, so percentage by volume, then here, so that's 5.75 milliliters of ethanol for every 100 milliliters of solution, and vice versa. And then, of course, with m/v, it's 4.8 grams of HCl per 100 milliliters of solution, and vice versa. Okay, now, again, I'll point out that we used grams here and milliliters here for questions A and B, where they have mass and volume, but we needn't have. We can use other units besides grams and milliliters. But for question C, where it's m/v, you have to use grams and milliliters as your units. Okay, So that brings us to molarity. Now, this is the really important type of concentration I mentioned earlier. This is just really useful to chemists because it helps relate moles of solute to the amount of solution. The amount of solution here being given in liters. All right, so molarity is represented with a capital letter M. So if you've ever looked at any of the bottles we use in lab and wondered what is 1M or what is 0.1 M, what does that mean? It actually doesn't have to do with the chemicals themselves, but it's talking about their concentration. Okay, so capital M is the symbol for molarity, and it's used interchangeably for moles per liter. Okay, so moles per liter or capital M are the same thing. Okay, so just realize you can interchange those. But specifically, it's moles of solute per liters of solution. Okay, so whenever you want to make up a solution, whether you're doing it by mass per volume or in this case molarity, you want to measure out your amount of solute by weighing it out, and then you want to bring up your volume to a set amount, right? But it has to be the volume of the solution. You don't want to measure your solvent and add it, because the volume of your solvent and the volume of your solution might not be the same. Sometimes your solvent, as it interacts with your solute, will actually contract a little bit. So if this is a 1 liter volumetric flask, if I filled it up, if I added 1 liter of water to this, it would actually not fill up the whole liter of this flask. Okay, but anyway, that's why we use a volumetric flask for making these solutions. Instead of measuring out the volume to begin with, we just fill up water until we get to the marking on the neck of the flask. That tells you you've reached the volume on the flask. In this case, if it's a 1 liter flask, if you fill up to that line, it's going to be, you've got 1 liter of solution in there. Okay, so that's pretty much how you make any solution in lab. You use this piece of glassware called a volumetric flask. So for example, if you wanted to make a 2 molar solution, or you want, in other words, you'd want to have 2 moles per liter, all you would have to do is, take your volumetric flask, measure out a liter, and then add 2 moles to it. So basically my point here is that we want to connect moles and liters, right? Again, like any good concentration, you are using this as a conversion factor to tie together amount of solute and amount of solvent. So so basically let's first see how we can solve for molarity. So let's walk through a problem together. What is the molarity of 0.5 liters of sodium hydroxide solution if it contains 6 grams of sodium hydroxide? So remember, for molarity, we need moles and we need liters. The question gives us the liters of solution, so no need for any conversions there. But notice that it doesn't give us moles of sodium hydroxide. It gives us grams of sodium hydroxide, and we need to convert that if we're going to solve this problem. So let's find the molar mass of sodium hydroxide. So using your periodic table, you see that sodium is 23 grams per mole, oxygen 16, hydrogen's 1. If you add those together, you see that sodium hydroxide is 40 grams per mole. Okay, and to save you some time, I've kind of written that here. So we divide by the molar mass and we get 0.15 moles of sodium hydroxide. Okay, now we have everything we need to solve the problem. We have 0.15 moles dissolved in 0.5 liters. So how do we find the concentration in moles per liter? Well, you literally take the moles and divide by liters. So you take 0.15 moles, divide by 0.5 liters, and you get the answer, which is 0.3 molar. Oh, by the way, this capital M, when you're saying this verbally, so as a noun, we're talking about molarity, but as a unit, you're going to use the adjective form of this, which is molar, like the tooth. So this is a 0.3 molar solution of sodium hydroxide. Okay, so why don't you guys try this problem out? So go ahead and pause this video and give this a shot. Okay, I'll point out that while again you've got the volume in liters, which is great, you aren't being given moles, you're given grams. So you may want to use your periodic table, look up the molar mass of potassium nitrate, and convert this to moles before you move forward with the problem. So when you do that, you'll see that the molar mass of potassium nitrate is about 101 grams per mole. So we should get about 0.344 moles of potassium nitrate. Okay, and again, this is not the final answer. Moles and molarity are not the same thing. Again, if you didn't get 0.344 exactly, that's okay. They went to more significant figures with the molar mass than you or I probably would. So our number would probably be slightly higher than that, but that's okay. All right, so we take the moles and divide by 0.225 liters, and there you'll get the answer. So you should have gotten something in the ballpark of 1.53 molar. Okay, and again, if you got something like slightly different, slightly higher, that's okay, as long as it's close. It's good enough for multiple choice. All right, so you can see that we've covered 4 different types of concentration, but they all basically work on the principle that we're looking at amount of solute per amount of solution, right? That's generally the gist of any concentration. So you need to know, looking at those units, what the units of solute and solution are. Okay, so with the 3 percentages, it's pretty straightforward, right? Mass per mass, it's going to be the same units of mass. With volume per volume, it's the same units of volume. With mass per volume, it's going to be grams per milliliter, per 100 milliliters, again, because these are all percentages. And then for molarity, of course, it's moles per liter. So you have to remember that. Just like the other ones, molarity can be used as a conversion factor. Molarity is moles per liter, so again, it's the number of moles of solute in 1 liter of solution. Please don't use 100 liters, it's not a percentage. Okay, so in this example here, we have 3.5 molar solution of HCl. What that tells us is there's 3.5 moles for every 1 liter, so we could write that out in our fraction. There's 3.5 moles of HCl per liter of solution, and vice versa. There's 1 liter of solution for every 3.5 moles of HCl. Okay. So let's use these conversion factors accordingly. How many grams of sodium hydroxide are needed to prepare 75 grams of 14% sodium hydroxide? So first look at that 14% m/m and ask yourself, what conversion factors can I get from that? What's that telling me about this sodium hydroxide solution? Well, if it's by mass, that means that there's 14 grams of sodium hydroxide per 100 grams of solution. Or vice versa, right? It's 100 grams of solution for every 14 grams of sodium hydroxide. So which of those 2 conversion factors are we going to use if we want to get rid of 75 grams of solution? That's where we're starting, right? So we want the grams of solution to be on the denominator of our conversion factor. Okay, so we're going to multiply by 14 grams of sodium hydroxide and divide by 100 grams of solution. That gets grams of solution to cancel out and leave us just with grams of sodium hydroxide, which is what the question wants us to find out. Here, why don't you guys try this one out? How many grams of aluminum chloride are needed to prepare 125 milliliters of 0.15 molar solution? So again, think about what your molarity gives you in terms of conversion factors. Okay, there may be some conversions you need to do, because notice that here they haven't given us liters, they've given us milliliters. Likewise, they're not asking us for moles, but they're asking us for grams. So there might be a few conversions we've got to do. Okay, so feel free to pause this video if you'd like to take a stab at this. Okay, so 0.15 molar tells us we've got 0.15 moles for every liter. If we have 125 milliliters, that's 0.125 liters. Okay, because there's 1,000 milliliters in 1 liter, right? Milli is 1,000th of something. So if we have 0.125 liters, how many moles is that? Would we multiply by 0.15 or divide by 0.15? Okay, well, we want the volume to cancel out, so we'd multiply by 0.15 because that's 0.15 moles per liter, per 1 liter. Okay, so you can see here that we would want to multiply by 0.15 and divide by 1 liter. Okay, and that gets liters to cancel out. Now, they've done this problem all in one line, but the next step, once you get moles of aluminum chloride, of course, is to convert that to grams, because the question doesn't want the answer in moles, it wants the answer in grams. So you would use your periodic table, look up the formula of aluminum chloride, you get something in the ballpark of, 100 and 133 point something. And basically, you would multiply by that molar mass so that moles cancels out, and you get your answer in grams. Okay, so you should get something in the ballpark of 2.5 grams of aluminium chloride. Again, you probably didn't get exactly this answer because you probably didn't get exactly 133.33 grams per mole, but that's fine. You probably got something close to this. Now, I mentioned that molarity is very, very useful because it deals with moles. And just judging from the last couple of chapters, you're probably starting to realize that moles are kind of useful to chemists. We really like keeping track of moles, right? It's a great way to measure out amounts of things. And just like all of our other stoichiometry that we've seen, we're going to use molarity to help us with stoichiometry problems. The only difference now is that to get into and out of moles, we're going to use molarity to get to, between moles and an amount of solution. Okay, so basically we're still following the same pattern as we did in literally every other stoichiometry problem we've done before. And that is get to moles. Like whatever you're starting with, whatever they want the answer in, that middle step is always going to involve a molar ratio, what this old Timberlake book referred to as a mole-mole factor. But basically, you want to get from moles of something you're given information about, and you're getting to moles of what you're being asked about. So let's see a problem like that. So here we have a reaction between zinc and hydrochloric acid to make hydrogen gas and zinc chloride. Okay, now let's see the actual question. How many liters of a 1.5 molar HCl solution completely reacts with 5.32 grams of zinc? Now, they're asking us about HCl. They're telling us we have 5.32 grams of zinc. So we are starting with this chemical, and we're being asked for information about this chemical. Now, what throws off students a lot about this question is they're like, wait a minute, we already have information about HCl. What, aren't we done? Isn't the answer just 1.5? Well, they're giving us part of the information. They're giving us the molarity, which relates moles and liters, and they want just the liters. So the piece of information you need to proceed with this problem is the moles of HCl, and that's where stoichiometry comes in. We can get to moles of zinc, from moles of zinc to moles of HCl using a molar ratio, right? That's a 1:2 ratio between those two chemicals. So first of all, we probably want to get moles of zinc. So you look up zinc in your periodic table. You see it's about 65.4 grams per mole. So ask yourself if you want to multiply or divide by that number to get from 5.32 grams to moles of zinc. Okay, so you want to divide by that molar mass, and that gives you the moles of zinc. That's your first step. Then, of course, your second step is to use that 2:1 molar ratio. There's 2 moles of HCl for every 1 mole of zinc. So we're going to multiply by 2 and divide by 1. Okay, and that gives us moles of HCl, which we can then cancel out by using the molarity as a conversion factor. Remember, 1.5 molar means that there is 1.5 moles for every 1 liter, or, to put it upside down like it is here, 1 liter for every 1.5 moles. So to get our, so our third step is to divide by this molarity, and that gives us the answer in liters. Now, please note that the question might not always want you to stop here at liters. It might want you to convert this to milliliters, in which case this is 108 milliliters if you multiply that by 1,000. Okay, so typically when I teach you, when we do stoichiometry problems together, I typically do this in 3 steps. Here they've actually done it all in one line, so you can kind of see the whole process laid out. But really, it's still the same 3 steps we learned in chapter 7, in chapter 8. It's the same 3 steps we saw again in chapter 9, and we're seeing it again here. The only difference is that we are using molarity to get out of moles this time. Okay, but it's the same 3 steps. We get to moles in our first step here, we use our molar ratio in our second step, and then in our third step we get out of moles. So you can see here that in chapter 8, we started and ended with grams at the most. Okay, though we could have gone from anywhere in this process For example, the question, instead of giving us grams, may have started us with moles, or instead of wanting the answer in grams, it might only want the answer in moles. Okay, but my point is that you had your 3 steps. You get from grams to moles, moles of chemical A to moles of chemical B, and then get out of moles, convert to grams. In chapter 9, we did this with gases. We used the ideal gas law, PV is equal to nRT, and we solved for N, that is the number of moles. Right? Or we sometimes use this shortcut if we were at STP, where if everything is at standard temperature and pressure, we know that 1 mole of gas occupied 22.4 liters. So the bottom line is that we were able to find moles of chemical A and get out of moles of chemical B and convert it again into a volume. Okay, but that middle step was still the same. We're using a molar ratio or a mole-mole factor to get from moles of chemical A to moles of chemical B. We just look at our balanced equation and just write down the coefficients of those to help convert one to the other. And then, of course, as you've seen just now, it's the same process in this chapter. All we're changing is how we get to moles or how we get out of moles. Molarity is that conversion factor that ties together moles of solute to volume in liters of solution. Since volume and concentration are tied together through the moles of solute, this yields an interesting phenomenon known as dilution. Basically, when you have a solution and you change the volume by adding solvent, the moles of solute doesn't change. So that ties together your molarity and your volume so that they are inversely proportional. Basically, as you add more of your solvent, you wind up lowering the concentration, also known as diluting the concentration. So just a little terminology here, and you probably are familiar with these words just from regular English, but essentially a concentrated solution is one that has a high concentration. You have a relatively large amount of solute and a relatively low relatively low amount of solvent, even though the solvent, of course, is the majority of your solution. Likewise, a dilute solution has a large amount of solvent compared to solute. There's very little solute and a lot of solvent, respectively. Right? So you probably have heard of those words, for example, with buying juice in concentrate. You can get concentrated juice, which just has solvent evaporated from it. You just evaporate water from it, so it ships at a higher concentration, and then you just add water to it to dilute it back down to the regular concentration. So for example, here we have a can of orange juice concentrate, and if you add 3 cans of water to it, it dilutes it to the same concentration as orange juice, but now you started off with 1 can and you've wound up with 4 cans of orange juice. So you see, this is a very convenient way to ship solutions. In fact, usually when we order chemicals, this is actually how we do it. If it's a chemical that we have to buy in solution, say an acid, it makes a lot of sense to buy the acid concentrated. I mean, obviously you've got to take steps to make sure you're shipping it safely, but you're kind of doing that with solutions anyway. So you typically buy your acid in a concentrated form, and then you can dilute it down to whatever you need to use in lab. All right. So for example, if you buy hydrochloric acid, you get it in like 16 molar or somewhere in that ballpark, and then you dilute it down accordingly, and you use, let's say, like 0.1 molar in lab. Okay. So we're going to look at how to do these dilutions. How do we tie together molarity and volume? Okay, so the key thing, again, like I said, is you have to realize that the number of moles of solute is not changing. You're not taking your solute out of the solution, nor are you adding more solute. The only thing that's changing here is the volume of your solution and the concentration. So remember, if molarity is equal to moles per liters, we can rearrange that so that the moles is equal to liters times molarity. Now, I've been using molarity as kind of an example, but basically this applies to any concentration in any volume. So instead of molarity and liters, I'm just going to use the generic concentration and volume. So basically, the concentration times the volume is equal to the amount of solute. Well, if the amount of solute is staying the same, that means your concentration times your volume before is equal to your concentration times your volume afterwards. So if you have a concentrated solution, we'll call that solution 1. Its concentration and volume is C1 and V1. And that's going to equal C2 and V2, which times V2, which is your dilute solution. All right, so essentially, if you have 3 of these 4 variables, you can solve for the missing fourth. So yeah, basically as you increase the volume, the concentration will decrease, and that's, but that ratio of volume times concentration will stay the same. All right, so let's try a problem out here. So here we have a solution that, we're starting off with 0.5 liters of 6 molar hydrochloric acid, and we're adding water to it. We're diluting it to a final volume of 1 liter. What's the new concentration going to be? All right, so your initial concentration, C1, is 6 molar HCl. Okay, that's how much we kind of, this is going to be our C1. All right, so if we're underlining all the important numbers here, this is our initial volume, this is our initial concentration. So this is C1 and this is V1. Likewise, this is going to be our final volume. So this is V2. The question is asking for our final concentration, which is going to be C2. We're solving for C2 in this formula. Okay, so think about how you want to rearrange that formula. How do you get C2 by itself? Well, you would have to divide by V2, right? So the slide here has used molarity instead of just generic concentration, but just realize it's the same thing, right? Here, the concentration is a molarity. So we're solving for M2, essentially. That's the same thing as our C2. But basically, we want to get M2 here by itself, so we divide by V2 to move it to the other side. Okay, and then we just plug in our numbers. So our initial molarity is 6 molar. Our initial volume is 0.5 liters. We divide by a final volume of 1 liter, and we get our answer of 3 molar. Okay, now of course this is kind of a silly example. You probably realize, like, oh, we've doubled the volume, so it makes sense that the concentration should be halved. But keep in mind that your numbers won't always be this neat. All right, let's try a different one. This one doesn't have molarities, and it uses milliliters instead of liters. So I want to point out here that the math is still going to be the same. We're still using the same formula. So go ahead and pause this video and take try this problem out. All right, so if you're back, probably see that again, if we look at our formula, C1V1 is equal to C2V2, we have a volume of 2% HCl solution, we have a concentration of 2%, and we're being asked for the volume for that concentration, and we're told that we start off with 25 milliliters of 14%. So this would be our V1 and our C1, so to speak. We're diluting this down to a C2 of 2%, and we're being asked to solve for V2 essentially. Okay, so remember, to find V2 by itself, we're going to divide by C2. So here's our setup for that. We have our basically our initial volume times our initial concentration, so 25 milliliters times 14%. And then we divide by our new concentration, the one we're trying to dilute to, 2%. And you can see that that gets those concentrations cancel out, and we're left with an answer in milliliters. Okay, please note that we didn't have to do any conversions here. We didn't have to convert milliliters to liters or anything like that, or convert our percentages into molarities. You see that as long as our units cancel out, we wind up with our answer in whatever units. Okay, now of course be careful of what the question wants the answer in. So if the question said it wanted the answer in liters, you would then have to convert this answer accordingly. Okay, your units for your answer are going to match the units of the other volume we're using here. Okay, go ahead and try this one out. All right, so here's your answer. If you want to check your work, you should have gotten 1.5%. So the question gave you an initial volume of 10 mils, an initial concentration of 9%, and it's diluting to a new volume of 60 mils. So we're solving for the new concentration, C2. All right, so you should have done 9% times 10 divided by 60, and that's gives you this new concentration. And again, if you want to check your work, just to make sure this makes sense, we're diluting the solution, so it makes sense that the concentration should decrease as the volume's increasing. So you know that your answer is going to be lower than 9%. Okay, here's another one you can try out. This one involves molarity. Okay, and that's going to be relatively easy since your concentrations in molarity and your volumes are in liters. Okay, so feel free to pause this. I'll go on and move on ahead to the answer slide so that you can check your work. Okay, so you should wind up with 0.2 molar as your answer for this one. Okay, again, we're diluting a solution, so the solution drops from 0.6 molar down to 0.2. Okay, I mentioned earlier in this chapter that while we focus on homogeneous mixtures, that's what solutions are, they're just homogeneous mixtures, we're going to look a little bit at some heterogeneous mixtures, namely colloids and suspensions. So the thing here is that a solution is a homogeneous mixture, a suspension is a heterogeneous mixture. Colloids are interesting because they're heterogeneous mixtures that look homogeneous. So this is a little different, right? They're kind of a little bit of both here, and they're a little tricky, so to speak, because of this distinction. Okay, so the key thing to realize here is that with solutions, your solutions have your solute completely dissolved in the solvent, right? You have these really tiny solute particles, they're completely dissolved, so they are evenly spread out, they don't really interact with anything that you can't really filter them out. They pass through semi-permeable membranes and so on. Colloids are interesting because they have suspended particles, just like a suspension. But the problem here is that these particles are so tiny that they spread out evenly through the mixture instead of just settling to the bottom, as you see in a suspension. So these particles are also so tiny that while while they are separated out by semi-permeable membranes, they also they cannot be filtered out. Okay, so while a filter will filter out suspended particles, in a completely heterogeneous mixture, these particles are so tiny they pass through the pores of a filter. Okay, which is, it's kind of confusing because you think that's how you would distinguish a solution, right, from a suspension. So you can't use a filter to determine the difference between a solution and a colloid. So the ways to figure out the difference between a solution and a colloid are, like I said, using a semi-permeable membrane of some sort. Okay, but there is one more test, and that is the Tyndall effect. Now, the Tyndall effect is something you've probably seen in just about every heist movie. When you might also notice it with powerful spotlights, at nighttime. But basically, what happens with suspended particles, such as those in a colloid, even if they aren't visible to the naked eye, they are large enough for light particles, photons, to hit them and get reflected, diverted away, some of those reaching your eye. So you can then see light being reflected. This is a key observation because light normally doesn't get observed when it's shining in a straight line that's not towards your eyes. It's not being reflected towards your eyes. So for example, if you shine a laser, okay, through air, which is a solution, right? It's a mixture of gases a homogeneous mixture of gases. So if you pass a laser beam through air, you will only see the beam of light when it hits a wall or some other surface, right? So you'll just see where the laser beam's pointed to, but you don't see the actual physical beam of light, all right? Um, However, if you can turn that air into a colloid by suspending tiny particles of, let's say, droplets of water by like using an aerosol to create a fog, you will then see the beam of light in your laser. This is where I brought in the reference to a heist movie. Like every time, the people in the movie are trying to break into the bank vault or whatever, that's highly, very securely guarded. They always have these laser tripwires for the alarm, right? And so you always have the people breaking into the vault taking an aerosol can and spraying it around, and that's where they see the lasers and they kind of avoid them, right? The spotlight example I was mentioning is if you have a very powerful spotlight, you normally see the beam of light, but that's because of things like dust and smog and other particulates in the air. Okay, that's why you're able to see a spotlight, right? If you had a spotlight shining in a completely clean, sample of air, you wouldn't actually see the beam of light. You'd only see where that spotlight hits, whatever surface it hits, because then photons of light bounce off that surface and go towards your eye. So you can see it there, but you wouldn't see the actual beam of light going from the lamp to that surface, right? So those are the two ways you can distinguish a colloid from a solution. So sometimes that can be kind of difficult. So the Tyndall effect and using a semi-permeable membrane is one way to do that. Suspensions are way simpler, on the other hand. Suspensions are heterogeneous mixtures that you can tell are heterogeneous, right? You can tell that there is something mixed in with your solvent. So, for example, we've talked about how salt and water is an example of a solution, or sugar dissolved in water. Muddy water is an example of suspension. Okay, so now the difference between a suspension and a colloid, of course, I mentioned filters, of course, that filters can filter out your suspended solute in a suspension. So if you have muddy water, you can filter the sand and mud and stuff and silt out. The other thing to notice is that in a colloid and a solution, because you've got something there like a solution's homogeneous, so everything looks like the solvent, and your colloid is, again, it's heterogeneous, it just looks homogeneous. So again, everything looks like a solvent in a colloid. In a suspension, you can tell there's something that's not your solvent in there. So with your muddy water, for example, it's not transparent like an aqueous solution would be. It's all cloudy, right? That kind of tells you that. Also, unlike a colloid where the particles are suspended evenly throughout the mixture, in a suspension, eventually, given time, your particles sort of settle to one side. So if you're in muddy water, if you leave it alone for a while and don't disturb it, the mud will settle to the bottom of your container. Okay, so if you want to keep it suspended, you've got to constantly keep on churning it. Okay. So those are the differences between a solution, a colloid, and a suspension. Again, I guess, like I said, the simple way to quickly distinguish them is that a solution is a homogeneous mixture, a suspension is a heterogeneous mixture, a colloid is a heterogeneous mixture where the suspended particles are so small that the mixture looks homogeneous. Okay, and as I pointed out, a filter will separate out particles from a suspension, your solute from a suspension, but that won't work for a solution or a colloid. A semi-permeable membrane will separate out the parts of a colloid, but that won't work on a solution. Okay, so that brings us to colligative properties. So we're starting to get into the last section of this chapter. So colligative properties are properties that change based on the concentration of your solution. Okay, so basically, examples can include vapor pressure, boiling point, freezing point, osmotic pressure, things like that. Okay, and so we're going to look at how these things change with concentration, how to do the calculations associated with them. Yeah, and in order to do that, we're going to have to learn a new unit for concentration, and that's molality. But I'm getting ahead of myself. Let's go break down why these property changes happen in the first place. Okay, the reason for collective properties is the interactions between solute and solvent. Okay, this changes the this kind of forces we're dealing with rather than just a solvent by itself, a pure solvent. Okay, so for example, when you when you look at a solution that has a dissolved solute, the vapor pressure for that solution is going to be lower than the vapor pressure if there's just a pure solvent. The reason for this, you could kind of think of the solvent particles, or the solute particles rather, as kind of clinging on to the solvent molecules, preventing them from escaping as a vapor. Okay, so that's kind of, in a nutshell, how collective properties work. They basically come about by these solute particles clinging onto solvent molecules, and that's what changes the properties of the solvent. So then it makes sense that as you increase the concentration of solute, this effect becomes greater and greater. You have more solute particles holding on to those solvent molecules. Okay. Now, the most common version of this that you guys are going to see, and that you might see in real life too, I guess, has to do with boiling point elevation and freezing point depression. Okay. For boiling point elevation, you could probably observe this actually if you just measure the boiling temperature of a salt solution, right? You could just compare that to the boiling point of a pure, just take some distilled water, or really, if you want to see the effect of just how these properties are collective, how they are dependent on concentration, you could take any sample of water. You could take tap water or whatever, measure its boiling point, then let it cool down, add a whole bunch of salt to it, and measure the boiling point again. And you'll notice that the boiling point is going to be higher with your salt solution, with the higher concentration of your salt solution. Okay, so that's what we mean by boiling point elevation. Okay, so again, think of it in terms of what those solute particles are doing. Those solute particles are holding on to those solvent molecules and preventing them from escaping as a gas. Now, that's what happens when a liquid boils, right? Essentially, you're going from the liquid phase to the gas phase. So if you have these solute particles holding on to the to your solvent molecules, it costs more energy to release those molecules as a gas. And this eventually translates into there being a higher temperature required. So when eventually they do boil off, it's going to be at a higher temperature. Okay. Now, freezing point depression has, it's the opposite trend. Your freezing point is lower than you'd expect, while the boiling point is higher than you'd expect. But the reason for it is still the same. Essentially, your solute particles are keeping your solvent in the liquid phase because they need them to be in the liquid phase to form that particular solution. Okay, so essentially your liquid phase is extended. By having your boiling point higher and your freezing point lower, you've got a wider temperature range that your liquid exists. Okay, and that's essentially, again, that's how these collective properties work in a nutshell. Okay, so you guys have seen freezing point depression actually probably every winter when when they salt the roads. The reason they do that is that adding the salt to any residual water or to ice that is melting basically lowers the freezing point of that water. So it won't refreeze into ice even if the temperature drops below freezing. Okay, that's the idea behind salting roads. Okay, so I mentioned earlier that to understand this, or to do the calculations associated with this, we're going to have to learn what molality is. Uh, but in order to get to understand that, I want you to think back to how electrolytes or strong electrolytes function versus non-electrolytes. Remember, strong electrolytes completely dissociate into their ions when dissolved in water, as opposed to non-electrolytes, which just stay intact as whole molecules. Okay? Now, weak electrolytes, of course, are in between. You have some molecules dissociating, but we're going to skip weak electrolytes for the most part, just because that would complicate the math a little bit for this. If you go into Chem 111 and 112, you may have to do calculations involving weak electrolytes. All right, but again, when it comes to your non-electrolytes versus your strong electrolytes, think about the moles of solute particles that dissolve. So in the case of a non-electrolyte, the ratio of solute is going to be the same, right? If you started off with 1 mole of sugar as your solute and you dissolve it in water, you will have 1 mole of dissolved sugar particles, right? The amount of solute does not change. With strong electrolytes, this gets a little bit interesting because your strong electrolytes split into multiple particles. Okay, so you're increasing the number of moles of particles overall. So let's look at sodium chloride as an example here. Sodium chloride, as we've seen, splits into sodium ions and chloride ions, right? Every strong electrolyte will split into some cation and some anion. In the case of sodium chloride, it's just Na plus and Cl minus. Now, if you have 1 mole of sodium chloride, if you look at this sort of balanced equation showing this, 1 sodium chloride gives us 1 sodium ion and 1 chloride ion. Well, those are 2 ions, right? We have sodium and chloride. The total number of ions there is 2. So notice that we've doubled the number of particles by dissolving our sodium chloride. Okay, for every NaCl unit that's trapped in a crystal structure, when it dissolves, it releases 2 ions, a sodium ion and a chloride ion. We have to take into account this increase in the number of particles when we do these colligative property calculations, because again, the more particles you have that are dissolved in your solvent, the more you're going to see this colligative property effect. So we have to take that in mind. So that brings us to molality. Molality, which I know sounds a lot like molarity, but it's molality. Its abbreviation is a lowercase m, not a capital M. Molality is actually very similar to molarity. In both cases, you're looking at moles of solute on the top of your calculation, on the numerator of that fraction. The only difference here is that we want to take into account the number of solute particles, not just moles of solute in general. Also, instead of dividing by liters of solution, we divide by kilograms of solvent. Okay, so this deviates a little bit from all of our other concentrations where we divided by some amount of solution. Here we're just dividing by the amount of solvent. Okay, and we're specifically using kilograms, which is a little bit rarer compared to some of our other calculations where we didn't do that. Okay, so yeah, so for those of you going on to Chem 111 and 112, you'll often find that sometimes molality is described, they instead of just directly going to moles of solute particles, they'll involve what's called a Van Hoff factor, which is the number of particles your solute splits up into. Okay, and so that's just for those of you who are going on to Chem 111, 112 and are maybe rewatching this to brush up on this stuff, this is kind of a simplified way of describing this, okay? So it's going to be slightly different when you get to Chem 111. Okay, let's do an example of a problem where we solve for molality. So here we're told that we have a solution containing 80 grams of the non-electrolyte glucose in 0.25 kilograms of water. Okay, so remember, to find molality, we need the moles of solute particles, and we need the kilograms of water. Now, the kilograms of water, that's pretty straightforward. The question tells us that directly. However, they don't give us moles of glucose particles directly. They just tell us it's a non-electrolyte, and they give us grams, which means we've got to convert that into moles. So we take our 80 grams, we're going to divide it by our molar mass of 180 grams per mole, and that'll give us moles of glucose. Now, remember, with a non-electrolyte, how many particles does that split up into when it dissolves? Okay, so non-electrolytes, of course, don't split up into anything. They stay intact neutral molecules. So the number of moles we get of glucose will also be the number of moles of dissolved particles. They just happen to be the same thing because we're dealing with a non-electrolyte. Again, if any Chem 111, 112 students watching this, it's because their Van Hoff factor is 1. Okay, one glucose molecule, when it dissolves, forms one dissolved glucose molecule, right? It doesn't split up into ions. All right. Well, once you have the moles of glucose particles and the kilograms of water, well, one divided by the other gives you the answer. So let's plug those in. Okay, so we take our 80 grams, divide by 180 grams per mole, and we get basically 0.44 moles of glucose particles. All right. Again, you might not get exactly that number with some rounding if you use 180 instead of 180.16, but that's okay. You'll get something close enough for multiple choice. Okay, but remember, that's not the final answer. We want molality, not moles. So molality is that many moles divided by our 0.25 kilograms of water, which gives us an answer here of a little under 1.8 molals. Alright, let's have a look at this problem. Now, here we have a strong electrolyte. So this is a good practice problem just to see how strong electrolytes affect things. So if you want to try get started on this yourself, I will point out that we have kilograms of water, so we don't have to do anything there. But notice that they're giving us 125 grams of magnesium chloride. So your first step, of course, would probably be to convert that to moles. So if you want to do that on your own, feel free to pause this video and try that out. Okay, just look up magnesium and chlorine in your periodic table. So if you've probably figured out by now that the molar mass of magnesium chloride is somewhere in the ballpark of 95 grams per moles. So we would take 125 grams of magnesium chloride, divide by 95.2, you could use 95 grams per mole, or if you want to be more precise, 95.21 grams per mole, and that'll give us moles of magnesium chloride. Now, here's where magnesium chloride being a strong electrolyte comes in. How many particles does this many moles of magnesium chloride split up into? Okay, so this is where you've got to consider that, that magnesium chloride being a strong electrolyte splits up into all of its ions. How many ions is that? Okay, so again, I'm kind of asking like, what's the Van Hoff factor in a way for those of you in Chem 111, 112? So magnesium chloride splits up into an Mg2 plus ion, and you get 2 chloride ions. So that's a total of 3 ions, okay, for a Van Hoff factor of 3. So in other words, whatever you got for your moles of magnesium chloride, you need to triple that. You need to multiply that by 3 to get the moles of particles that we're going to use here. Okay, so we take our 125 grams of magnesium chloride, divide by 95 grams per moles. That gets grams to cancel out, and we are left with moles of magnesium chloride. We multiply that by 3, because there's 3 particles per mole of magnesium chloride. That gets rid of moles of magnesium chloride, and we have basically somewhere around 3.94 moles of particles. Now, of course, then comes the last step. We need to take our moles of our solute particles and divide by our 0.5 kilograms of water, and that gives us the answer. Okay. So, what do we do once we calculate molality? Well, molality is the concentration we use to figure out colligative properties. So you multiply the molality of your solution by a particular constant, and you can figure out how much the boiling point or freezing point is going to change. Okay, so let's look first at freezing point depression. Okay, For freezing point, for every 1 molal solution, your freezing point is going to drop by 1.86 degrees Celsius. Okay, so that's basically your constant for your conversion between um, molality and change in freezing point. Okay, so it's essentially the same thing as negative 1.86 degrees Celsius per molal. Okay, that's another way to look at that. Likewise, for boiling point elevation, the constant would be 0.512 degrees Celsius per molal. But this is a positive number because, again, your boiling point gets elevated. Okay. This, of course, that's the constant for water. So you're going to have to assume that water is your solvent there, which, to be honest with you, in this class, it pretty much always is. Okay, so let's see an example of this. A 1 kilogram sample of water contains zero point 0.5 moles of sodium phosphate. What is the freezing point of the solution? Now, sodium phosphate is a strong electrolyte. It's a sodium salt. It will dissolve in water. So how many ions will that split up into? Okay, so our Van Hoff factor there is going to be 4. We have 3 sodium ions plus a phosphate ion. Okay, so if you have 0.5 moles of sodium phosphate, 4 times that amount is 2 moles. What you actually have is 2 moles of solute particles. So if you take that and divide by your 1 kilogram of water, that should give you the molality. Okay. Now, knowing that the freezing point drops by 1.86 degrees Celsius per molal, you should hopefully be able to figure out what the new freezing point of the solution is. Okay. Hopefully you guys got negative 3.72 degrees Celsius. Okay, so if we have 2 moles of particles for every 1 kilogram of water, that's a molality of 2. So we take our 2 molals, multiply by negative 1.86 degrees Celsius per molal, and that gives us a change in temperature of negative 3.72. Now, please note, the change in temperature that you just calculated is not the same thing as your freezing point. Okay, you have to, at least mathematically, they're not the same. Numerically, they happen to be the same because luckily the freezing point of water is 0 degrees Celsius. So you're just subtracting that number from 0, and so it happens to be the same number. Okay, now for boiling points, that's not as lucky. Okay, so let's have a look at what happens to the boiling point. Well, the molality is still 2 molals, right? And we saw earlier that our boiling point constant is 0.512 degrees Celsius per molal. So if we multiply those two numbers, we see that our change in boiling point is 1.02 degrees Celsius. Okay, so now this is where having that change, making that distinction between change and actual boiling point is kind of important, right? Because if the question asked you for the boiling point, and you said, oh, it boils at 1.02 degrees Celsius, what would be wrong with that answer? Okay, think about how weird that sounds, right? Water boils at 100 degrees Celsius, and you're saying that this solution, which should boil at a higher temperature, is boiling at 1.02 degrees Celsius. That's significantly lower than 100 degrees Celsius, so that there's something wrong with that answer. Well, again, when you do this calculation, you're not getting the boiling point, you're getting the change in boiling point, delta T for B, for boiling. So if the question asks you for change in boiling temperature, that's fine, that's all you need. But if the question asks you for the actual boiling point, don't forget to add that answer to 100 degrees Celsius, which is the normal boiling point of water. Okay, so for this particular example, the water would boil at 101.02 degrees Celsius. Okay, when we try this problem out, okay, just a good practice problem for you guys. So now this question says to find the freezing point. I would recommend, if you want some extra practice, try getting the boiling point too. I have both answers on the answer slide to this. Okay, so hopefully pause this to try this out and you're back now. But basically, we have 0.5 moles of calcium chloride, which calcium chloride is a strong electrolyte, right? So what does that split up into? Well, you've got calcium ions and chloride ions, but there are two chloride ions. So our Van Hoff factor here is going to be 3, right? 1 calcium plus 2 chlorides gives us 3 moles of dissolved particles. So again, we can take our 0.5 moles of calcium chloride, multiply it by 3, and so that tells us how many particles we have that are dissolved in the water, right? And then, of course, we can multiply by that constant, negative 1.86 degrees Celsius per molal. Okay, and we find out that our boiling point rise is 2.8 degrees Celsius. Our freezing point drop is negative 2.8 degrees Celsius. Our boiling point, of course, though, you have to do that calculation separately. Instead of having negative 1.86 here, you have plus 0.512 instead. And you'll probably find that the boiling point rises by 0.77 degrees Celsius, though since the question asks for the actual boiling point, you've got to add this to 100 degrees Celsius. And so the actual answer is 100.77. Okay. Another application of collective properties is osmotic pressure. Okay, we're going to see how the concentration of a solution is going to affect this osmotic pressure. But first, in order to understand this, I should first explain what is osmosis. Now, you probably are already familiar with osmosis, but if not, if you've heard of diffusion, osmosis is just the diffusion of water. So you're trying to get, just to jog your memories if you haven't heard of diffusion in a while, diffusion is the movement of material from a higher concentration to a lower concentration through a semi-permeable membrane. Okay, so in this case, if you have your water moving from one region to another, that's what osmosis is. Okay. All right. So basically, if you have two solutions separated out by a semi-permeable membrane and they don't have equal concentrations, they're going to keep on equalizing until their concentrations get more or less equal. All right. So your dilute solution is going to leak water into your more concentrated solution, trying to dilute it down. Okay, so here's an example of that. So we have a 4% starch solution on the left and a 10% starch solution on the right. And they're separated by a semi-permeable membrane. So starch is a colloid, and so it won't pass through the membrane. Now, of course, water is a small enough molecule to pass through the membrane. So what's going to happen here? Which solution has, relatively speaking, more water? Well, the 4% starch solution, since it has a smaller percentage of starch, that tells you that it's got a higher percentage of water, right? So water is going to move from that container on the left into the container on the right, trying to dilute it down. And it's going to keep on doing that until both concentrations are equal. Okay, both are at 7%. Though in order to have 7% on the right, since that side has more solute, its volume also has to increase accordingly.
Now, an interesting thing to note here is that water isn't intelligent. It doesn't know that the concentrations are even. What we're seeing here is what we call a dynamic equilibrium, which is something we're going to go into in a little bit more detail in the next chapter. But basically, the rate of flow of water from one side to the other, or from the left to the right, is going to equal the flow of water from right to left. Okay, before, so if I go back a slide, when the concentration was uneven, when we had more water here on the left, because there was more water, there were more water molecules just hitting the semi-permeable membrane and making their way through. Okay, it's just a concentration thing. There's more water on this side, so it makes more sense that more water is going to be forced across. All right. Again, this is kind of what drives diffusion in general. So once you get to this point where both concentrations are even, now the rate of water going from one side to the other is going to be the same as the rate of water from the other side going to the first, because the concentrations are even. So Osmotic pressure is a way of kind of describing this. It's kind of a way of quantifying uh, water needing to diffuse to offset a difference in concentration. All right, we describe this as osmotic pressure. So basically, you could describe it kind of as like the pressure that would be equal to opposing this flow of water. Okay, the pressure you would need to stop it. Basically, it's another way to look at it. If you want to define which side has the higher osmotic pressure, a higher concentrated solution will have a higher osmotic pressure because water wants to flow into there to dilute it down. Okay, so when we're defining which two solutions have a higher osmotic pressure, it's the more concentrated one, the one that is more solute, because again, like I said, water is trying to flow into there to dilute that down. So osmotic pressure could be described as the pressure necessary to prevent that. Okay, let's see if we can do a couple practice problems that tie that together. So let's say we have two solutions, a 10% starch solution that we labeled A and a 5% starch solution labeled B. And of course, it's separated by a semi-permeable membrane. So which of these two has a greater osmotic pressure? Right? I kind of mentioned that the one with a higher concentration of solute will have a higher osmotic pressure. Okay, so you should be able to answer question 1. Now think about how water is going to behave here. Okay, how will these two solutions behave? And see if you can answer questions 2 and 3. Okay, so pause this if you need a second, but you can see here are the answers. So water is going to flow from solution B into solution A. All right, because again, remember, solution A has a higher osmotic pressure. It's a higher concentration. Water wants to flow into there, right? And dilute that down. So basically, our 10% starch solution will dilute down to like 7.5%. Our 5% starch solution will lose water and get concentrated up to 7.5% as well. And at that point, you'll hit an equilibrium and water will stop flowing. So at that point, then, what will happen to our water levels? Well, our water level of solution A will rise because water flowed in there to dilute it down, but our water level of solution B will be lower, right? Because it's lost water because it flowed into, the container, the half of the container that had solution A. Okay, so that's why the level of solution B will be lower. All right, so basically the process of opposing osmosis, okay, if you have a pressure that's greater than your osmotic pressure, you can essentially kind of go against this natural diffusion process and kind of force one side to become more concentrated than the other. Okay, now this is like I said, we call this reverse osmosis, and it has its uses. Sometimes we do want to concentrate stuff, or as the case might be, in the case of desalination, we want to lower the concentration of solute. We want one side of our container to have more water, because that water then is purer water. So if you're taking seawater, which has a lot of salt dissolved in it, typically, that's a relatively high concentration of solute in there, but seawater is it's very abundant, right? So if you are in a situation where you don't have a lot of access to fresh water, right? Using reverse osmosis on large quantities of seawater will help you get fresh water out of that. Okay. Now, of course, this is very energy intensive. It's definitely not easy. So you want to make sure you have no other options, right? But that being said, this is one way you can kind of get fresh water out of seawater. Another application of this osmosis affecting systems, this tendency of water to want to move from a region of higher concentration for the water, so a more dilute solution, to a more concentrated solution that has more solute and therefore less water. is, from a health standpoint, a health sciences standpoint, we see this a lot in cells. All right, this is the reason why when you give a patient a saline solution, you've got to make sure that it matches the concentration of their blood, right? Because water will leach out or oversaturate, uh, you know, your patient's cells if they don't have um, the right saline solution, right? So let's use red blood cells here as an example to see what happens to cells in general when they're put in different types of solutions or in solutions of different concentrations. So when a red blood cell is placed in a solution that has the same concentration as the contents of that red blood cell, okay, we call that an isotonic solution. The prefix iso means same or even, right? So an isotonic solution is one that has the same concentration as the contents of that red blood cell. So if you're trying to make that, do that with uh, let's say an IV solution, the equivalent here with sugar or salt would be 5% mass per volume of glucose or 0.9% mass per volume of sodium chloride. Okay, either one of those describes the kind of concentration you need to have the same osmotic pressure, to match your red blood cell. Now, for healthy red blood cells, they kind of look like this. They're kind of round with a kind of dimple on both sides. Like you can't see the underside of it, but it also looks like that. So it's kind of like a little compressed disc. The little dimple in there increases its surface area. That just allows it to exchange oxygen a little bit more. Okay, so this is what a healthy red blood cell looks like. Now let's look at what happens when we put it into solutions of different concentrations. If your solution is too dilute, we call it a hypotonic solution. Now, the word hypo means less than, all right, lower than. So the concentration of solute is lower than that of the cell, which means there's, relatively speaking, more water in that solution. So what happens is water starts entering through the cell membrane. Your cell membrane is a semi-permeable membrane, right? So the water starts flowing into the cell, trying to dilute it down. And the problem with this is that it kind of, your cell can only take so much water. You reach a certain point where your cell starts taking in so much water that it essentially bursts. Now, this process is called hemolysis. Hemo, the prefix hemo is the prefix for blood. Okay, that's where you get the word hemorrhage from, right? A hemorrhage means to leak blood, right? The word lyse, the suffix or prefix there, means cut or to cut. So hemolysis is the condition of red blood cells being sort of cut or broken. And of course, then we can have a hypertonic solution. Hyper means greater than or higher than. And so a hypertonic solution has a higher concentration of solute, which means it has, relatively speaking, less water. So water flows out of the cell in an attempt to try and dilute it down. The problem then, though, is that the cell starts to shrink. It starts losing water, and it undergoes a process called crenation. Okay, I don't know if there's a Greek root behind that, like there is with hemolysis, but that's what crenation is. It's when your red blood cell basically shrinks because it's losing water. So let's try some practice problems that go over that. Okay, so first of all, remember if you're looking at a glucose or a sodium chloride solution, if you have 5% glucose, actually, if I go back just to show you that we have a 5% glucose solution, mass per volume, or 0.9 mass per volume of sodium chloride, those are what we need for an isotonic solution. Okay, so let's label each of these as either isotonic, hypotonic, or hypertonic. Okay, and again, you can use that prefix hypo to know that we're talking about a lower concentration, and hyper to mean a higher concentration than isotonic. Okay, so take a second and label these. Okay, and if you've joined me after pausing this video, there are the answers. Okay, so you can see that the 5% glucose solution at the bottom here, that's an isotonic solution, right? With the first one, 2% is greater than 0.9%, so this is a hypertonic solution. our 1% glucose is lower than 5%, so that's hypotonic. Likewise, zero point 0.5 is lower than zero point 0.9 for sodium chloride, so that's also hypotonic. Okay, let's have a similar problem here. Now here again we have solutions, and you want to ask yourself, are these iso, hyper, or hypotonic? And then accordingly ask yourself, would a red blood cell placed in this solution not change, undergo hemolysis, undergo crenation? Okay, and you remember that each of these conditions is tied to the concentration of your solution. Okay, so if it's isotonic, it won't change. If it's in a hypotonic solution, so there's more water, the cell is going to absorb water and undergo hemolysis. If it's in a hypertonic solution, so there's more solute and therefore less water, the cell is going to lose water to the surroundings and therefore undergo crenation. Okay, so again, take a second and identify the each of these solutions and identify them as iso, hyper, or hypotonic, and then accordingly choose the right condition for them. Okay, and so here are the answers so you can check them out. Of course, the 5% glucose solution is isotonic, so it doesn't change. 1% glucose is less than 5%, and 0.5% of sodium chloride is less than 0.9. So both solutions 2 and 3 are hypotonic, so those cells will undergo hemolysis. And of course, 2% sodium chloride is greater than 0.9, so that's hypertonic, so that cell would undergo crenation. Okay. And that's it for this chapter. So here's some practice problems to try out for homework. As always, just let me know if you have any questions. Of course, feel free to do any other questions that are similar to these if you want some more practice. And thank you for your time and good luck.